indirizzo, account e tutto, è stata segata.
Non le fanno più, non lo vogliono. Noi stiamo combattendo quelli della segreteria? Le ditte. Parliamo.
Noi abbiamo dato l'indirizzo di posta elettronica Gmail e praticamente Rottini sta usando l'account di Colomba. Non ce li fanno.
Quello della specializzazione.
Ti avete consegnato pure le borsette? Al seguito, infatti, devo comprare. Ne devo rifare uno nei 91, adesso abbiamo fatto uno sempre. Al centro di casa.
Da me è arrivata la notifica della mail student che l'avrebbe ricevuta e poi mi sono specializzato. E io attualmente uso il mio anno perché non me l'hanno ancora vista. Quindi ancora potendo usufruire la mail. Non so poi se succederà da un momento
A un
all'altro.
certo punto, da un momento all'altro, te lo disabiliti, no? Perché quello fanno veramente. Di solito un periodo che va da 6 mesi a un anno dalla fine del tuo corso per la disabilità, no? Però tu, essendo assegnista, hai che ti ritrovi sì, Alba è assegnista. Sì, poi tu vai su rubrica doppiata e metti Gaia Potenza e spiega perché.
Poi dovrei chiedere, probabilmente la passare tramite Pasquale. Quindi metti un po', magari aperto via Pasquale, io ho fatto una bella mail, bla bla bla, e ti metto un po'.
No, prima la fai subito, così magari se l'hai prima che stai quella, poi cominciamo a darti una docente. E se poi ti trovi il video senza questa potendo anche non ti ma poi una che tu sei in sé, ma anche frutto che dai, non è un dico mazzo che
No, no, è possibile. No, non andava
quella no, tu non hai fatto la campionata di sicuro che ho fatto questo anche per la reina che
Gaia Potenza. Ti ho mandato la foto, non perché ti farti vedere la posizione strategica. No, anche mi dà un urto di nervi. Sì, è proprio una cosa. Stessa cosa. È bravo, qualsiasi cosa, cosa ti muove. Poi.
Io potrei fare e si basta. Io vorrei verti valori che ho molto di viaggio, però si scende.
valori che qui ce l'ho poi che si la parte di oggi
Della settimana si fa. Per esempio,
fanno tutto a 360 gradi, certo che se tu li facessi, come si fanno la professione, se fate la polizia, Covid,
per esempio,
una cosa così, penso sì, è bene. Poi se tu ti racconti come è stato modificato, come era il tuo lavoro in un'oretta prima del Covid e che procedure per salvaguardare voi avete adottato con il Covid. E tu mi dicevi che avevate uno che stava per poi passare da un po' di quella che
sì, quello è stato uno studio, è l'unica
cosa che mi ricambio. Sono abituato a questo, è stato
il dottorato.
L'ho ridato nemmeno io, è poco etico.
Il collega ha fatto la tesi che
Va bene,
Non l'ho fatto io, l'ho fatto il collega suo.
se no attraverso la probabilità.
Prendi ha messo Gordon Fioc nel sedere di cadaveri per 3 anni.
Un anno.
Un anno? Comunque tanto. Sono tanti culi,
che culo.
Per la scienza questa.
E non lo hanno fatto questo non sa perché.
Ah no?
Ma no, dai, ma sono fatto per il lavoro che ha fatto.
È vero, sono d'accordo.
Ma che brutta persona.
Più benissimo.
Ha fatto pure quel bel paper, quanto tamponente. Storie di Clovis.
Storie. Chronicles.
Covid, cosa?
Covid.
Devo fare ingegneria. Non c'è bisogno di stare in mezzo ai computer. No, io so, perché mi hanno raccontato diversi tuoi colleghi, che le procedure per proteggervi voi dai cadaveri che erano morti di Covid sono state diverse rispetto a quelle canoniche di un'autopsia pre-Covid.
Sì.
Quindi se tu...
Per esempio che la sala, per esempio, settore del Vergata è stata esclusa dall'autopsia. Per cui comunque si deve descrivere il protocollo.
Devi descrivere il protocollo e puoi anche dire, facciamo l'esempio che Tor Vergata questa cosa non la poteva fare perché non era idonea, cioè racconta un po' di storia vissuta.
E poi faccio anche sul...
Quella è una cosa che sicuramente non gli racconta.
Questo è un ottimo. Presta attenzione, questo è un ottimo consiglio. Loro vedono sempre se tu racconti cose che hai fatto o che hai detto. Quindi se trovi il modo di collegarlo, anche se insomma, è tutta roba che hai fatto, ma insomma se trovi il modo di collegarlo su qualcosa che hai fatto, ti stanno per te.
Considera che poi lui c'ha l'ultima ora della giornata, quindi
Per quello
c'ha 17-18, quindi è
Di tutto.
è laureato in relazioni.
possono vedere foto di rimangono stupore.
Allora, gli arabi sono un po' delicati sull'argomento,
Sì.
non troppo.
Qualcosa di non troppo.
Non nudi possibilmente, non hanno problema con i defunti, ma con i nudi.
Beh, non è vero, anche no.
Vabbè, sono poliziotti, Alba, i morti
No,
li vedi.
non sono poliziotti. Non sono
Ci stanno pure i
poliziotti.
poliziotti.
No, sono protezione civile.
Va bene, comunque i morti se vanno in emergenza li vedono pure in protezione civile. Quindi metti anche qualche foto di qualche cadavere. Il problema che in passato hanno avuto, la conosci la biondona, la Bruzzone, no? Lei fece vedere molte foto di casi su cui aveva lavorato, dove i cadaveri però erano nudi, e c'erano nudi di uomo e nudi di donna. E le donne hanno problemi, comunque l'ha fatto. Le donne del Middle East avevano problema a vedere le foto del nudo di uomo e viceversa, gli uomini a vedere le foto del nudo di donna. Quindi se c'è il cadavere, no, il nudo sicuramente abbiamo già visto che un qualche imbarazzo, perché loro devono essere uomini con uomini e vedere solo foto di uomini nudi, capito? Donne con donne,
il polmone macroscopicamente
sì,
un polmone da una
quello va bene,
per far capire che comunque un danno macroscopico.
Non so come hanno fatto in Marocco, che hanno fatto una slide e sono usciti tutti i vitelli con le bolle del monkeypox. Questo non lo devi fare.
Sì.
Durante e voci di fumo,
Sì.
con le bolle del Marocco, che è strano poi.
Gruppo di due.
Erano marocchini, però era un ospedale militare, attenzione, quindi avevano.
No, la scienza fa dei piselli.
Sì. No,
Io
no.
metto sul tesserino.
Anche purtroppo bambini coperti.
Anzi, l'ho rivisti, ce n'è uno che è identico a Alba e uno che è identico a me.
C'è avuto un insomma di zanzara, poi me l'ha visto lui. Lui praticamente si è arrabbiato tutto qua e gli ha avanzato l'occhio. Ma soprattutto io mi preoccupavo perché si era alzato tutto l'occhietto, no? Il fatto che era lui, ho sentito anche la vediamo, ma noi tutti la stessa cosa, prendi il vento da uno, taglio la umidità, gliel'ho dato, si è fatto la vediamo, glielo devi dare assolutamente, si vede che si gonfiano le labbra e ha problemi a respirare, detto che se gonfi sotto l'occhietto ci sta perché il pizzico ce l'ha qua, comunque io mezza cosa di vento non è che...
Anche che era bello sfogo,
Sì.
per non si zanzara.
Che poi insomma la crema, quindi per loro si crea.
Pure sulle braccia si vede che hanno un'iperattività. C'è un'iperattività proprio.
Però l'hanno ereditata dal bambino.
Quello è tutta della mano.
Fare il prick test,
Sì.
le prove alle bugie.
Le buttate?
Magari adesso la leggiamo allora qualche ristorante alimentato, qualcosa così.
Prendi il caffè, io adesso fa l'acqua, la guardia lava, così mi è andata a fare una passeggiata con mi ho portato un caffè.
Sto di martedì. Ma anche a porti dell'aula. A tornare
veramente una problema. No, mi è andato nel panno e mi dico, no, mia madre mi metteva questa scioppa, quasi mia mamma. Mentre mia madre, ma guarda, sempre gonfiato qua sotto l'occhio. No, però io no, vabbè, sì, è più gonfio, pure più rosso questa striscia. E tu però mi sta grattando, gli ho messo la crema e quindi figurati un po', vabbè. E si può, oh Dio, come lo vedo in vedere? Me lo dico a lui, sai, Gabriele, in macchina, alla macchina, là sotto, sali 5 piani, lo fai vedere. No, perché mi spiace.
Ma poi io devo stare a casa mia. Lo zio, no?
Chi è? Sì. Però dico che quarantena. No.
Mio cugino.
E la ragazza non
È la moglie.
Mi sei andato in casa abbastanza.
No.
No, non lo voglio. Ma mi forza.
Grazie. Le mie creature.
Le classiche piccole vesti che non mi entri in sintonia rimangono lì. Perché?
Sì. Tipo, se stai in un'altra ora là.
Era bello che si faceva.
Sembra che gli è venuta una cosa che non torna.
Mi sto chiedendo.
Ma no, te lo faccio vedere poi ti dici, vabbè.
Perché tu gli hai fatto un'incisione per me quest'ora? E detto il taglio.
No, ho tagliato il pentolo, mi ricordo meglio la sticca di pentolo.
Ah, ero sconvolto, sinceramente.
Bravissimo, vero? No.
Avete riduso l'occhio a essere.
No, perché cazzo?
Ma dai! Chi è? Era gonfio?
Alla sera non l'hai visto?
Ma che non l'ho visto? Ma che non lo chi è? Ecco.
Due reazioni forti.
Hanno visto più leggi e l'abbiamo salvato.
Lo devo pensare!
Ricoverati d'urgenza.
Ma la sera non ti serve, è bellissimo.
Roberto ha fatto un cadeau.
Chi è?
Luccione, questo non è canale.
Tu vuoi fino al corso di misure nucleari, no uno.
Vabbè, io ho sempre più.
Poi dedicato alla canzone. E vedi come stanno liccione.
Mi piace per buono sì.
No,
È bello il tempo poi, vero?
no, questa settimana invece di farmi fare
Poi capire scena ancora.
falla così.
Fortuna sono quelli alleati. Ma tu sei chieto? Perché tu no.
C'ho voglia di
No, anche perché non vecchio soltanto.
sta finendo. Deve fare un esame, ora tu nel base, ora lavoro in linea come ingegnere non sei,
Sembrano creati.
lavoro in linea a Giulio, in Basilicata del Brasile, il padre di questo ragazzo.
Simone è la Toscana di
Sì,
il Garigliano?
Garigliano, che c'è?
Ah, aspetta. Trisaia.
Sta
Trisaia.
non
Ora mi confrontiamo. Poi non Brasile.
Pisaglio.
sì, è giù.
Polipora.
A Trisaia c'è l'Eneco.
Pisaglio sono
Allora è Pisaia, non stavo confondendo io. Alba, non me la devo venire di pace. A me tutto il caffè preso.
Caffè si vende?
Sì, ma io non voglio andare al bar a fare la fine. Quindi aspetto che Alba
Dove?
Guarda.
Dov'è?
È proprio libero.
Anche quello che non voleva sentirsi dire.
Avevo nera la gamba con la ragazza di non c'è nessuno.
Ah, c'è il bar qui dentro, no?
Aspetta. Ah, bravo.
Mi fai autorizzare per
Sì.
ricordi di te che ci aspettiamo noi. Identici. E io non sai a che appartieni. No, è palese. Il centro nazionale medicina. Ah, ok, io sono davanti con Roberto. Sì, poi Roberto. Roberto Perna ormai non lavora più di vista difesa civile. Voglio Sergio con Roberto. Sergio. Allora, noi siamo pensati. Sì, tra l'altro, devo dire anche una cosa. Domattina mi è sembrata una piccola presentazione sugli strumenti di canzone, solo che hanno organizzato tutto in 4 mesi. Perché se no dividiamo la grossa in 4 quindi come ti comporta? Cioè rimangono tutti e 4 Ah no, tu fai il docente, non vieni dietro noi. Tu stai con i tuoi e fai il docente. C'è un problema per la presenza. No, stai là, facci docenza, stiamo scherzando. Poi ti fai il giro dei cavalli. No, ma tra l'altro l'ho visto. Fai casa tua. No, 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 tu resti in impostazione dove ti mettono la presenza deve essere.
Per un po' in carità. Per niente, non lascio detto
Da tipo, sempre la maglia, la forma,
Come dire, no, ma chi sto come dire, altri figli sono.
A che partito?
A chi appartengono? Chi è parte?
Andiamo su allora. Poi facciamo.
Anche come troppo prima vabbè,
No, perché pensavo che magari mi stai rispondendo perché non lo sa. Perché praticamente
no, che l'ho proprio guarda, non ci sta pagato, ho proprio
pensavo che l'avessi ascoltato, però mi avete risposto perché non ho ancora risposta. Praticamente Colomba mi ha detto, io ho chiesto no, mi devono convocare perché mi devono comprare, perché mi si cioè, mi hanno mandato il fatto.
questo servizio è sempre. Non so se basta una comunicazione che abbiamo fatto o se fisicamente devi andare a firmare il contratto o se te lo devono mandare per posta. Facciamo passare questa settimana qua.
Sai perché c'è sempre bene perché devo fare il supplemento del concetto di casa. Io ho l'accettazione.
Basta l'accettazione.
Sì, però magari non mi c'è scritto davanti del corso di questo.
E allora possiamo.
Questo il vocale devo chiesto, ma si può fare una sorta di tipo di dichiarazione da allegare a questi codi in cui
Oh sì, io la posso proporre io. Io ti posso mettere che sono 24.000 euro non saranno banca. E adesso te lo posso scrivere io. Vai. Very well. I was busy with my son this morning. For 20 minutes a week. Okay. Everything okay? Somebody knows that, right?
Yeah.
But still something is missing. The Bahraini guy. 3 of them they have to come. I feel that
we saw them on WhatsApp, but
they have a workshop in Manama. They will join us next week or no later than September. But, and then this is the class.
But they have to stay 6 months here, right?
1 year.
They
1 year.
1 year?
They have the ticket, they arrive 17 May 2025, and the departure is 1 May 2025.
When we will get our grades for the report? Our grades for the report.
You will get it in June, because, yes, we will, we did ask the lecturer to revise all the report because it's first level and second level. So there are 4 modules for 2 classes. It's a lot of homework to correct. We asked them to send all the results by the end of June. So by the end of June, you will receive the first grade of the first part of the course. For this one in May, the end of October, because we will assign it at the end of this week and the end of next week, and we will give you till September to deliver it. And then end of October and beginning of November, you will have the results of it. It takes a little bit because you are a lot of person.
Yeah. We were shocked about the markets. We didn't know.
We were sure
We saw in the group only 2.
they didn't allow us to add them in the WhatsApp group till today. So we will add everybody this afternoon or tomorrow morning.
They are all in festival or not?
Then first, 6 and 7. It is the renewal of the professional agreement with the Abu Dhabi. We knew that they had to send some money. Honestly, we were a little bit surprised when we received that. Yes, but the number of the students is class has to be maximum 40. We are less than 40 by regulation, so it's okay.
Yeah, that's okay. See you.
See you, bye bye, enjoy your break. One of my other friends. Language barrier
quindi scienze, perché
Noi siamo tutto tema scienze perché ci hanno dato l'aula lì, mercoledì siamo in economia perché ci hanno dato l'aula lì e poi da giovedì fino a venerdì della settimana prossima siamo in economia. Poi c'è dalle 14 alle 16 emergenti importanti.
troppe
Sì, poi il professore che era questi seminario, chissà, come poi è per poi da 95 anni fa l'ex moglie del figlio è stato lei la mia poi dalle 2 alle 4 c'è emergenze, piani di emergenze per le cose come grandi e dalle 4 alle 6 controllo. Poi sempre quello che si vede in questo poco di studenti grandi. Però è essenziale. Sì, non in questa
invece queste settimane
solo poi o altre 2 settimane insieme, ma prima di questa per raggiungere
la settimana
sono in numero, sono una guerra il secondo, che proprio per due.
se perché fa protezione
Io volevo sapere di una versione che fa, chiacchierare che ci facevamo ora. È carino che racconta cosa è cambiato nel suo lavoro dopo il Covid, perché non si è trasformato il suo lavoro a causa del Covid, perché è stato una delle emergenze biologiche più grandi che ci abbiamo avuto dalla seconda spagnola. Quindi, visto che è rimasto il CDRN, lui deve raccontare di se stesso in chiave emergenza.
senza biologica.
L'emergenza paziente in questo caso è una cosa recentissima e quindi se racconta quel punto di vista che ho preso. Grazie.
Se ne fa differenza. Allora, c'è questo grande dubbio, tu manchi. No, nemmeno si
Dovrebbe essere vai a dire dieta ma neanche con il cibo
specialmente dopo il secondo generazione che è quello che mi ha detto che serve.
Penso ci fosse esatto. Andrea mi raccontava che i laboratori li aveva fatti dei frutti, anche quelli della parte così, tutti gli esperimenti. E quindi quello è il lavoro che si somma a quello di laboratorio che avevate prima. C'è il Giappone, c'è l'America.
Il tuo laboratorio come
La scuola Polvani. Dopo l'andiamo, lo faccio vedere. Tanto è quasi tutto sposato. Anche se ho detto che le live che ho preso perché poi a giugno bisogno di un laboratorio per degli esperimenti che io devo ricordare, se non mi dà una stanza. Quindi quello è bastato non sapendo e non leggendo pure nessuno. No, farmi dare le chiavi della stanza. Però di fatto lo inizio a usare nel corso finché non prendo qualche progetto. Quindi parlavo per esempio con Giacomo Mangiagalli che mi diceva che loro per esempio volevano iniziare a dare un kit dimensionale quello di carne o le sorgenti naturali. Quello per fare qualche esercizio sulle statistiche di conteggio intanto è carino, però tutte le classi le ingegneria e medicina di misure se li porto a fare qualcosa di quello che vediamo in slide
I siti che abbiamo.
No, sappiamo. Quando c'è solo questo. Questa stampa, non
Capito? Anche gli altri.
Intendiamo il gruppo loro.
Evidente.
Sì. D'accordo. No, settimana prossima ne andiamo a mangiare una pizza.
Sì.
Pure quelli che non fai. Portiamo questo gruppo dei 20 così non è male a posto.
Casino sta alla conferenza.
Allora, ma detto che i documenti li avete fatti tutti, perché non c'è il dubbio che questi non si scrivono, scrivono, scrivono.
No, qui non hai capito. Allora,
Quando cominciano?
i prossimi mesi, però la prossima, le prossime moduli in presenza.
Settembre.
Sì, ma è scritto di scrivere.
Cosa ti interessa?
Relax.
La parte dei 45K. Interessava.
Oh, guarda che bella.
Bella. Sì, sì, però altri 45 qua sopra che stanno
No, nel meglio.
minimo giorno continuo.
Ce l'ho.
Keep going.
Keep going, infatti vado.
Faccio un
Che fai? No. Ah, non mi viene niente.
Ciao, ci ridici chi sei?
Io?
Sì. Io sono scarso di me, come faccio?
Non ho capito.
Sono scarso di
Non si ricorda
non mi ricordo.
Emiliano Franci.
Esatto.
Ce lo potevo presentare io questo.
Settimo?
No, io lavoro al centro, il centro tecnico di
Non ti fidi? Ma dici, ma
al centro, sì.
Non mi ricordo.
Sì, sì, al centro.
Piacere di
Piacere,
Proprio avete l'inizio che ti dà un giudizio.
Quindi invece dobbiamo
Io sono direttore delle macchine, quindi teoricamente per un servizio.
no, mi sa che non ha parlato con
No,
me.
perché la prima volta non venni perché c'è stato un...
Non sei venuto da
No, alle prime settimane di febbraio non venni.
Ecco perché c'è un volto nuovo. Non
Sì,
stai qui dentro.
non venni perché c'era, insomma...
Era capito chi doveva
Misunderstanding.
chi doveva
Sì,
pubblicare cosa.
basta Toscana, vicino a tu.
Ok, ok. No, per questo non,
No, è chiaro.
non riconoscevo il volto, ma ha ragione tu, non l'avevo mai
Sì,
visto.
sì, certo. Non è la prima settimana non vengo, non venni, ma non per mia volontà perché non c'è stato...
La storia la conosco tutta quanta, perché non sapevo che tu eri quello.
Sì, ero proprio lui.
Se basta che abbiamo risolto. Benvenuto.
Era sentito al 100%?
No,
Sì.
no,
Poi si sente.
pensavo di Belluno, perché insomma poi è
Poi si
tutto
sente.
scani.
Sì?
Lui, vabbè, sì. Io nato mamma di Luca,
Ma
Ah,
però l'ho
Pure a
sentito.
te non è che non si sente per niente, eh?
si deve sentire.
Molto.
Ci ho fatto caso,
Deve
si
sentire.
Quindi
non si sente per
come... No, sempre, io l'ho chiesto, io l'ho chiesto. Però non è come il tuo, è diverso.
È molto diverso,
È
certo.
molto
no,
di transizione verso voi. Verso voi.
Detto, vabbè, lui è proprio
Io
libero.
poi sto ancora più giù di perché io sto proprio sul confine con l'Azio. C'è
Molta contaminazione.
sì, molta contaminazione.
No, io sinceramente non ti avrei messo questo.
Dalla fibra in giù è più Lazio.
Attenzione occhio perché te già una volta devi stare con quell'altro.
Con quell'altro che ti ha detto che te eri
Ti ho
nel
detto del
contatto.
contato, te lo ricordi?
Sì, molto.
Punto.
Molto male.
Cosa ti hai riportato alla
Poi,
mente?
Lui è figlio è fratello d'arte.
Sì.
poi pensavo quando ho detto quella cosa, ho detto,
Bene, sono legato al suo fratello nell'ambito AI.
Sì, me ne hanno parlato spesso di arte, perché ho visto che insomma anche il professore non faceva parte, ne ho approfittato subito. Lo devo dire per
Beh.
No, però continua ad essere
E Valentino.
consiglio a piazzarti nell'Azio, sai.
No, non
c'erano sempre colori, molto bello, guarda lì.
cioè, poi
Contento lui?
Con gente
Contenti
professore,
da ieri più che mai.
Oh, bello. Meglio.
Com'è?
pantalone
Domani giallo-rosso.
Ah, Milano.
ovviamente come sto scherzando. Oh, ovviamente blu, dai, un attimo per me.
Allora, che c'è? Però,
Poi in finale Coppa Campioni, devo mandare il messaggino il giorno che si gioca.
ascolta,
Non lo senti.
quella è l'ultima umiliazione.
No.
Siete forti.
Ieri ci è ritoccata la maledizione Lazio.
Siete-
Per un attimo si era rientrato in gioco lo scudetto, era l'unica cosa che si poteva vincere quest'anno.
Allora, se
No, era l'unica cosa.
dai, non è il Paris Saint-Germain, non è forte come il Manchester City. Però.
No, quest'anno mica assolutamente.
Poi magari prendete
Tutti i
qualcuno.
derby. Ha perso la competizione.
I derby poi l'abbiamo persa con Bologna, no?
Sì, ho capito, ma i derby l'ha perso.
Ma non sono i partiti che abbiamo vinto noi. Poi è una bella squadra, bella allenatore.
C'era il mazzo, aveva già appena fatto.
Infatti al Milan ne ha fatto più un po'.
E li faceva il mazzo. Perché il punteggio non è.
Posso rubare un po' di
Guarda che c'hai le prese sotto tutti i banchi, questa è elettrificata. Hai sia il cavo che il collegamento internet che le prese, praticamente ogni due posti c'è una presa. Poi se la vuoi attaccare da te, attaccata da te.
Veramente una bella.
Questa è bella. Poi facevo fisica e scienze motorie.
Piace.
Manca secondo me come in Fleming il microfonino che tu hai qua, perché stare fermo
Non andiamo, quindi messa il becco. L'Apple.
non lo so.
No, ma comunque io cerco di stare abbastanza davanti al microfono, spero.
Oh, no, c'è stato bene.
Mi ha detto di sì, sì.
Lei la sta seguendo,
Sì.
sta seguendo in remoto.
Ma io mugisco, questa è un'altra cosa, che parlo mica a voce. Parlo a voce, insegno senza microfono.
Ma qua magari serve perché per vedere bene lo schermo bisogna stare su. Effettivamente se stai su un microfono aiuta.
Il problema è quello che per vedere lo schermo, magari usare il puntatore,
Devi venire qua.
devi storcere
Prendi il
tutto.
coso.
No, beh, no, perché vabbè, va tutto bene, va tutto bene.
Senti, se devi usare la lavagna, hai il gessetti lì. E la...
No, ogni
La-
tanto mi
quella
serve,
singola-
ma mi piazzo così di squincio e magari sto attento a.
Buongiorno.
Tutto bene?
Bene. Grazie.
Non vedo cosa
No, siamo passati dall'altra per le regia e lunedì mangiamo fuori, ci dovrebbe avere l'aspettata. Ho passato tutto il sole lì.
Siamo a Pirovia, andiamo dal nord, non siamo abituati a questo gatto.
Una volta, sì, ormai.
Ma dove? Da quale nord venivo?
Torino.
Biella.
Il nord
C'è
proprio.
il sole, proprio.
Ma vai,
Non c'è. Non c'è
non
arrivato.
c'è mai però.
Là non c'è il sole.
E da qualcuno con la lampadina che mi fa così sulla città, ho capito? Il faro del porto. che-
Non c'è il sole.
Oh, io penso che
Candidato a Torino 3 giorni. Quindi, insomma, questo è il livello.
volevo dire. Lorenzo, di nuovo di telefono sulla.
Ma no, non è così che sono lo chiedi un'altra volta
Ah,
stasera.
Non credo.
siamo dritti per dritto, dici.
Domani sarò da Sorboni, sono solo due. C'è stato mercoledì semmai. Io aspetto a Roma, se non mi risponde non li faccio per niente a 470 euro andata e ritorno per Milano.
Sono d'accordo con te.
Perché se poi me ne
Dobbiamo fare attività inoppisitabile, no?
400, sì.
475 euro.
Andate e ritorno online. Allora, dobbiamo fare attività a Milano gratis per l'oppositabile. La facciamo da anni. Una TTX in un piccolo corso di 20-25 persone che loro fanno per i tecnici di laboratorio chimici che vengono dai paesi dell'Africa. Ok? TTX l'abbiamo iniziato a fare quando c'era il Covid in telematica e poi sono sempre andate Mike con Colomba, Mike con Alba, Mike con Riccardo, sempre due persone. Quest'anno ci approvano una persona sola e l'approvazione per la missione singola arriva mercoledì della settimana scorsa. Noi giovedì ti scriviamo e gli diciamo siamo sempre venuti in due da Tor Vergata perché per fare una TTX con 25 persone vanno fatti almeno due gruppi e servono due.
Sono 4 gruppi.
Comunque servono almeno 2 persone, perché se una sta lì a spiegare e coordinare ci vuole almeno un facilitatore. Siccome ne abbiamo sempre mandati 2, no, ma noi la missione a Torto non l'abbiamo fatta perché veniva a Varese. Sì, quest'anno però a Torto non ce abbiamo 2 persone che vengono da Roma. Quindi la seconda persona, se non può venire, non viene nemmeno la prima. Le ho detto a questo è oppisidabile, perché rischiamo di fare una figuraccia e siamo arrivati a un punto in cui una figuraccia con 20 paesi dell'Africa non la vogliamo fare, visto che abbiamo i master
Ma
internazionali.
anche Brasile, cioè, non so fare di paesi.
Che cosa succede? Succede che oggi mandano l'autorizzazione alla seconda missione, ok? Mandano l'autorizzazione alla seconda missione, ma sul foglio di autorizzazione che loro mandano c'è scritto che l'autorizzazione copre fino a 220 euro di spese di viaggio, no? Ma oggi per mercoledì con l'aereo,
Non
perché
costava anche la settimana scorsa 220
sì,
euro.
Oggi per
premessa.
questo mercoledì.
Dopodomani.
Capisci?
L'altro problema che c'è, molto semplice, è che non gli hanno autorizzato la notte, ma la missione in giornata, perché vengono da Roma e l'attività inizia alle 9. Allora vengo, aspetta, allora io vengo in aereo se devo stare lì alle 9 a fare l'attività fino all'1. Però l'aereo, se tu me lo autorizzi il lunedì, per il mercoledì viene 4,70, non 2,20. Quindi lei gli ha scritto: mi rimborsi 2 biglietti da 4,70, se no non veniamo, perché sui fogli c'è scritto che tu mi rimborsi il
Io ho
2,20.
detto, ho visto anche il treno che sta a 2,60, ma non arrivo in tempo per quello che devo venire.
Il treno pure a questa cifra arriva.
Sì, ma oggi per domani,
Volevo
no.
Ma dove viene fatta? Milano dove?
Cioè che è anche vicino sia da Linate che da Milano Centrale, 3 chilometri. Cioè non è che poi devi fare il viaggio. Però se tu la fai
2 notti in albergo e 2 biglietti del treno.
facciamo il martedì sera, dormo, faccio
2 notti intendo per 2 persone, scusa. Una notte, 2 per notti, vai.
And the problem is that you need to be left dalla area. 46 anni fa la macchina quando la prendo la strada, pure 45. Peccato, vedi?
Ah,
Cioè,
alla pizza. Io 28 aspetta, non c'è il modo
no, per casa nulla, effettivamente non è stato ci stava e beh, oh, dove sono tutti fissi a lezione di scienza.
Sì, con questa colonna te la tua lettera. Metto sempre quella di vivo, quella del prestazione di vita. Poi allora sto parlando del dubbio, poi il due facciamo. Arriverà nel paese.
perché poi che non fai questo ah beh capito basta hai un leggero ma se il primo giorno ah sì io entro nel fuoco perché ho preso sto penso che ho governato sul Facebook and leggere la roba so
a start of
e si mette a 13 mentre vado a fare la e qualche spirito
non funziona prima, devo scrivere oggi.
per
Con quello
Quindi era
ho scoperto stamattina e tu dovresti avere la domanda, ma c'è appunto deve essere uscito fuori e poi
l'ultimo della
Scusiamo, se facciamo questo test mi dici che pure prima se non conosci me.
non ci sei arrivato qua. Quindi entra di sapere me la faccio, li seguo, per giorni così possono no, io non lo dico, però no? Anche loro hanno delle liquidità. Ho visto solo piacere
Il minuto il tempo ho sentito che comunque collaborazione mi si è fatto anche del film comunque all'interno dei dipartimenti di legge e era giusto per capire se nell'ambito dello scopo ci sono stati fatti degli studi su tumori alle gonadi questo perché diciamo che in questi anni ci sono state denunce per quanto riguarda le cause cardiovascolari. Però essendo che dal punto di vista della chiaramente un tumore se è venuto per cause ambientali, non si possono distinguere. Il tumore delle gonadi è intanto un organo radiosensivo, il coefficiente del motoidote, che è per 27, è più lento. No, il tumore delle gonadi è quello che diciamo è selettivo per lavoratori per individui al di sotto dei 40 anni. Quindi si sa che è una soglia di età. A sopra i 40 anni difficilmente sviluppa il tumore delle gonadi proprio perché così. E quindi lì chiedevo se, data la radiosensibilità comunque dell'organo che comunque anche ha e poi il fatto della vesicoglia
Interrompere. Il fattore di peso è basso non perché si abbassa la sensibilità, è basso perché è relativamente facile la diagnosi, quindi la terapia, se la diagnosi è fatta presto, la viene suppressa. Lo sai benissimo, il fattore di peso nei tessuti,
dai 2 minuti per comunicare questa cosa all'inizio posso dire non
dicevo, I documenti, la risposta botta così.
Perché io mi immagino che è uno dei pochi lavori che se avviene in quasi perché già avete lavoratori tra 40 e 60 anni
Mi permetto di distillare un dubbio.
assolutamente, assolutamente.
È un tumore solido. Ha una latenza 20 anni, forse di più. Secondo me, perché quando sono stati esposti prima di iniziare a lavorare, perché il sistema riproduttivo, tra l'altro, anche la pubertà
Io se lo vuoi usare, io non so
se vuoi arrivare a difendere il datore,
entrambi, a dipendere da datore di lavoro.
se si manifesta prima dei 40 anni, può suggerire una specie di sensibile 10-15 anni.
Io ti sono cioè i 50 e 60 anni. Se non tumori sono azione 50-60 anni, non esistono tumori a 50-60 anni. Veramente parlo degli uomini, perché le donne no, diciamo che dal punto di vista della meno di 40 sono è quello che si sviluppa nella popolazione normale. E quello che al di sotto di 40, oltre dopo i 40, il tumore alle gonadi non ha più
non è gli stessi dicendo che o insorge entro i 40 o uno praticamente
questo nella popolazione normale, nella popolazione normale che non si entra
mentre i
in
lavoratori sì.
no, i lavoratori no, non ce ne stanno. Allora, mi sono proprio espresso male. Nella popolazione normale, al di sotto dei 40 anni, tipicamente si può avvenire il tumore alle donne. Ovviamente parlo di popolazione maschile perché alla popolazione femminile, guarda, io lo so che avviene anche sessualmente. La popolazione maschile, se mai studiato l'incidenza dei tumori oltre i 40 anni, perché quello, a mio parere, sempre da lettore, potrebbe essere una diretta correlazione con le attività che si svolgono. Però io quando ho visto, lavorando in ONE in questi 15 anni, le cause professionali, avvengono cause o per i polmoni, o cause per eventualmente il colon o altro, che ovviamente non c'è, nessuno può mettere la mano sul fuoco sulla correlazione. E quindi mi chiedevo, ma c'è stato mai uno studio perché quello effettivamente accidentali una persona normalmente non ha un tumore al colon del sistema. Quindi sì, sì, vabbè, parecchi corridori ce l'hanno, viaggiano tra i 20 e i 30 anni.
Esattamente.
Quindi,
Continuo a pensare come risposta mia botta e senza valutazione che ora sto cercando, che potrebbe essere correlato alla fase in cui una maturazione del sistema riproduttivo nei maschi, perché in quella fase sicuramente c'è un'attività cellulare maggiore che potrebbe corrispondere a una maggiore sensibilità. La domanda diventa, sì, ma io anche adesso mi sono esposto.
anche perché poi il fattore di peso delle gonadi poi è anche un po' particolare rispetto agli altri, perché è una somma di effetti cromatici ereditari, quindi mentre agli altri che la radiosensibilità lì invece tiene conto di entrambi gli aspetti, sia alla persona che quindi
Questo è ridotto per relativamente facile possibilità di diagnosticare. Quando cresce un feto, se anche uno non mette la testa sotto terra, insomma, e si nasconde al problema, non conosce quelli che si fare piacere perché non si può qualcosa di anomalo, di no, vabbè, Tanta gente che si manda paura di sentirsi dire, paura di sentirsi dire adesso tu no.
Va bene, grazie.
Io faccio questa comunicazione e ti lascio no. Can we restart?
Sta registrando ancora.
Tutto.
Perché avevo un attimo dietro perché non voleva vedere se la deciso dico provare
So good evening, everybody. Just a couple of communication. For those who I am going to see the first time today, welcome. I am Andrea Malizia. I am the director of the CBRM Master Courses. Just a couple of technical information. Somebody is delaying. After 15 minutes of delay, the tutor have to cut the hour of presence because the students have to wait, the lecturer, not the lecturer, the students, okay? We have to start, you have to stay here at 2 p.m. This is the first communication. Second communication, regarding the internet connection, you can use all the digital service of the university, included the internet connection. Once you have completed the enrollment and you have done the authentication online, you will receive a document. Inside the document, there is also an email, your name, your family name at students@uniroma2.eu with a password. You can go online, change the password, and with that email, you can connect to EduRoam. EduRoam is education roaming and is a service of internet connection you can use in all university and research center all around the world, okay? And then you have also a series of services, included the possibility to download the package Office 365, so you can download Team, Excel, PowerPoint, Word, and you can have a VPN, a free VPN. And if you go on the website that is called agevola@uniroma2.it, you can find the website in English and Italian language of all the discount you have in all the shops in Rome and around Rome for travel agency to buy tickets, book hotel, going to the gym, going to the mall, shop for the clothes, electronics, and so on. This is for all the students. You have just to bring a printed copy of the document in which there is the authentication that you are students here. You print it, you put it in the bag or in the wallet, And every time you go in one of that shop, you have from 5 to 30% of discount. So when you are here in Rome, you can use it, okay? No other communication to do, just please, you have to stay in class in a proper time. We will change building tomorrow and Wednesday. Tomorrow we will be inside the building of science. You will receive all the information on WhatsApp by the end of the day. Wednesday we will be at the Faculty of Economy. And from Thursday till the end of next week, we will be again here at the Faculty of Medicine, with the exception of Friday. Friday we will go to visit the firefighter atomic laboratory that is close to the university. By the way, every night we will send information for the day later with the position and where you have to park, okay? Now I leave the floor to Professor dErrico for his call, okay? If you have some question, it's a good moment to do it. Curiosity, please. Good question. Thank you so much. Yes, with the email address of Tor Vergata, you have the access to all the editorial book company that are that have published a paper or a book. Springer, Elsevier, EOP, Nature, the Lancet. So all the most important one. For instance, inside the Elsevier, you have, I think, 32,000 of scientific journal. Inside Springer, you have 22,000 of scientific journal. You can access inside, you can download all the paper for free with that. You can download the books, you can download the paper, and this is the legal way to do. Then there are also non-legal way, but I am recording the lecture, so I cannot explain it. But by the way, you can go for the legal with email, okay? You do not need to go, okay, with email or such systems. It is not necessary. Questions? Oh, okay. I leave the floor to Francesco for the second part of the lecture. See you at the end of the day. Bye bye. Grazie Francesco.
Buoni esami.
Aspetta.
Se l'ho messo io così perché stia un po' più inclinato.
No, così come.
Lo faccio io dopo. Ti rimetti nei capi.
Qual era questo?
Sì.
Ok, allora.
Da qui c'è il raggio.
Perché non mi dà più. Vedi? Da qui non me lo dà. Non capisco perché. Lo possiamo richiudere?
Perché condiviso.
No, ti rimetto io la condivisione. Aspetta. No. Ah. Non è questa?
Questa chiudila pure.
E ce l'abbiamo sul connetto.
Lo sto facendo la vendita. Poi farà il rilascio.
Questa?
Ah.
Ok. A te. Lo schermo è condiviso, sta registrando a posto.
Bene. Okay, any questions? You're abandoning me. Oh. Any questions on what we said before? Questions, doubts, curiosities, anything? No. No? Yes? Maybe? No?
Understand about the outline, how to detect the outline of the decay of a substance of the.
Experimentally. So with radiation detectors, you follow the decay. Depending on the type of radiation, depending on the half-life, you can do that more or less accurately. For example, a difficult one to measure accurately is the half-life of radium-226, being 1622 years. It's a very, very long. So you need extremely good statistics. Then you'll be able, with measurements that last years, you'll be able to see something that is statistically significant. Isotopes that have a shorter half-life are relatively easy to monitor. Oh, the half-lives are published, yes. I thought the question was, how are they determined? And the reply is experimentally. Yeah. Okay, let's restart slowly so that when the, yes.
Between the activity of the material and the absorbed dose. Because one say the number of disintegration per second.
Yeah.
Second is energy per kilograms.
Right.
And so one is in the domain of time and the other is in the refer to the point.
Okay. So the answer is, when you know the flux of charged particles, you can estimate the dose, the absorbed dose, or other quantities that we will introduce now. When you know the activity of a given substance, you must also know the geometry of the radiation. That is, whether it's an external exposure to that source, or whether it is a source that has been incorporated. In that case, there are models that account also for the biological excretion effects. Because what you incorporate, you not only lose because of physical decay, but also because of the biological decay, as it's called, which is treated as if it were an exponential. Not exactly true, but as a first approximation is what everybody does. Now, each one of the different molecules that are labeled with radioactivity, because see, the point is, when the radioactivity is administered in nuclear medicine, very rarely it is the isotope that is administered directly. What is administered is a molecule that is labeled with the isotope of interest, because the molecule has the role of targeting the tissues or processes or organs of interest. So the biokinetics, so to say, are really dictated by the biochemistry of the molecule. And again, it gets a bit complicated. There's a way to describe the body as with compartments that exchange these materials. But yes, the models do exist and are constantly being refined and expanded to include the new pharmaceuticals, the new molecules that are labeled with different radiopharmaceuticals. So again, it really depends on the nature of the source, and the complexity comes from internal contamination.
So you have analyzed case by case.
Yes.
Not don't have a general relation to.
Well, there's a general
relation.
formalism, but then it gets declined in very different ways for the different isotopes and molecules. Yeah. I can gladly let you have some material if you're interested that you can look at. Will do. Yes.
Studied, for example, that gamma wave can be transformed into two particles in certain conditions. But my question is about the dualism wave particles. So how I can be sure that gamma wave is a wave and
from one point, it transforms in particles. And I don't know if you understand my question.
Oh yeah. So the dualism between undulatory nature and particulate nature of radiations is a theory that's been well developed. De Broglie has developed all this, and there is experimental evidence. So, for example, there are detectors, even relatively old systems such as bubble chambers. They were able to show the conversion of the production of pairs of electrons. The detectors were operated inside a magnetic field, and they were irradiated, and then you would see the appearance of two spirals. That's the experiment that Rutherford did to document the existence of a central mass and charge in atoms. That is an experiment where alpha particles were scattered by a gold foil. So it's an interaction I have not described. I have shown the alpha particles as depositing energy through collisions with electrons. You have to understand, I only have 8 hours. And as much as it looks like a lot of time to you, to me is very, very little. So I'm trying to focus on the things that I believe are most relevant. But again, I'm also available to discuss these things separately if you wish. Point is, these things are in part theories, in part experiments, and often they have verified one another. For example, this is a good example. The early measurements of energies of the beta particles showed this continuous spectrum that I plotted. That continuous spectrum was initially a big mystery because the neutrino could not be detected, or the anti-neutrino couldn't be detected. So it was theorized that it had to exist. It was the only possible explanation. The theory was there was consensus that it had to be there, but again, until some evidence was acquired, the final proof wasn't available. So it's always like that. Yeah. Stochastic effects. So we've talked about deterministic effects, those that occur above certain dose levels or thresholds. And then there are those that can actually happen with any exposure above 0. But they don't happen for sure. They happen with a certain probability distribution. The probability is considered to be proportional to the dose, something that is also not fully demonstrated, or at least it's not demonstrated at very low doses. For high doses and high dose rates, as it says there, the dose-response relationship is known. That is also true for the survivors of the atomic detonations over Hiroshima and Nagasaki that have been followed. They are being followed throughout their life. But what we don't know is, at least not for sure, what happens at very low doses. At very low doses, there are many of those that are called confounding factors. That is, the same type of consequence, the same type of cancer may come from a variety of other environmental agents. And the other thing is, it's very difficult to detect, as it says there, small increases in cancer rates. I'll show you what the sample size should be when you're looking at very, very low doses. A further complication comes from the fact that the natural incidence of cancer, and by the way, natural incidence doesn't mean spontaneous incidence. Cancer is caused by something. What that something is arguable, but it is a natural incidence in the sense that it's not directly correlated to a known additional exposure. That's high. It's over 20%. Fatal cancer. Keep in mind that cancer incidence is about double that because cure rates are in the order of 50%. So 40% of the population does develop cancer. About half of it dies of it. Or if you want to, let's look at the other part of the glass. Let's look at it fully partly full, half of them get cured. And many of them are cured also thanks to the use of radiation. So what do we have? We have data from different sources. The main source is the analysis of the survivors of the nuclear detonations over Hiroshima and Nagasaki. It's by far the largest cohort of adults and children and pregnant women with similar characteristics, not similar to ours, similar within the cohort that has been analyzed. But as you can see, there's a variety of other sources of data. Some of them are pretty disturbing. You may know about the radium watch dial painters. There were two main factories in the United States where in the 1920s and 30s, mainly ladies were painting the hands of watches and instrumentation for aircraft with radium-loaded paints, so that in combination with other materials, it would fluoresce, it would emit light. And the sad part is that to paint the hands of these devices, they were using brushes that they were licking. So they were dipping the brush in the paint, painting the hand, the dial, and then they were licking the brush to make the tip thin, and then they would dip it again. Now, radium is a bone seeker, so it caused a lot of bone cancers. Thousands of cases have been observed. In the 1950s and 1960s, the Navajo Indians in Arizona were in their reservations, but they were given the opportunity of a lifetime to work for pretty decent pay in uranium mines. That was supposed to be a good job. The problem is that uranium mines have a lot of radioactive gases inside of all kinds. So they developed a lot of lung cancers. Early medical radiation workers didn't know what was going on, so they were putting their hands in the beam, the X-ray beams, all kinds of things, and they were developing cancer. Enlarged thymus glands were treated with X-rays in the 1940s and 50s. There was this excitement about radiation. They were using it for anything. They were even using it to treat acne, pimples in the face. I had a friend when I was a student in the United States in the 1980s. This was a professor. So I studied at Yale University. That's where I started my career. And I lived with a family. The guy was a professor of Greek, wonderful person. He had books everywhere, including in the bathrooms. But the guy had a very strange skin on his face. And once he told me that as a teenager, he had been treated for acne with radiation. Yes. I mean, it worked, but who knows what else it did to him. And, you know, there was a time when in the States in particular, they were using X-ray sources for anything. You would go to buy shoes, and to make sure that your foot was fitting well in the shoe, they would do an X-ray of your foot. So you would see with the shoe on, you would see if your toes touched the tip of the shoe. It was crazy. We have data also from the evacuees of Chernobyl, but the dosimetry is not as accurate as what we now know for the survivors of the Japanese blasts, so the Hiroshima and Nagasaki. So let me tell you a bit about those. There were about 300,000 individuals that survived. And of those 200,000, 300,000, as it says there, for some 100, 120,000, in fact, with a very long, painstaking process, it was possible to reconstruct the dose. It took a long time. Of these, about half received doses higher than background, so they were analyzed as potentially meaningful. It's by far the largest group, and it also included almost 4,000 pregnant women. Let me show you, they've been followed and the cancer incidence has been documented. So this is the map of these two cities. As you can see, the distribution of those around Hiroshima is much more uniform because Hiroshima is on flatlands. It's on the sea in a fairly flat region. So the dose expanded laterally, almost unimpeded. Nagasaki, instead is in a very narrow valley. The detonation in both cases was caused between 600 and 800 meters from the ground. That was considered a way to maximize the effects. Because on the one hand, they didn't want the blast to happen too far from the ground. Of course, there is reduction due to the divergence of the beam, sort of 1/r reduction. But on the other hand, the more vertical the radiation was, the less shielding from the buildings would take place. If you make something detonate on the ground, buildings will block some of the blast. So their optimization was to make them detonate, as I said, between 600 and 800 meters. You can see the population of these two cities combined. There were about 600,000 people, and roughly half of them, in the end, were wiped out and have survived. Here you see a map that documents the regions that got more or less than 5 milligray. So once again, you can see how the distribution is affected by the geography of the places. Now, reconstructing the doses was very, very difficult. Obviously, people were wearing no dosimeters. Obviously, there were no monitors distributed in the place. So it was done primarily through a phenomenon called thermoluminescence. Thermoluminescence is a phenomenon whereby certain materials, typically certain crystals, trap electrons after they've been irradiated. And these electrons can then be freed from these traps by heating up the materials. When the electrons are freed, in the process, they release some light. So I had a video here, but because I wasn't sure that it would run on this computer rather than my own, I've taken a couple of screenshots. These are two examples. These are quartz samples, but again, similar to the type of materials that were investigated. The materials were ceramics. So in Japan, their houses were not built like ours, but they had a lot of chinaware. So cups, dishes made of porcelain that is a thermoluminescent material. Here you see what happens when the quartz crystals or pieces are being heated up. They start emitting light, and at some point, there's actually an intense flash of light. So as you heat them up, they emit light. Of course, these are not dosimeters, so they were examined, heated up, light was measured, and then the very same pieces of ceramics were irradiated to known doses of radiation to sort of calibrate them. It's a post-calibration process. And thanks to this and a lot of complicated analysis, it was possible to reconstruct the doses. The complication came from the fact that the two weapons were different. One released more neutrons than the other. Something that also explains the fact that cancer incidences were different in the two cases. Neutrons lead to the release of heavy charged particles that are more biologically effective. These are studies where you see for different age groups, the effects in terms of, in this case, it's reported in terms of positions. So people who were very close to the epicenter, what would now be called ground zero, I guess, and higher distances. You see the distribution in terms of ages and in terms of their genders. And here you also see, that's an interesting, no. Sorry, I thought I had selected another slide. I don't have it here. I have a slide where the number of pregnant women is reported, and it's a fairly high number. It's about 3,600, which if you correlate it to the number of people examined, is a high percentage of population that was pregnant. In the Western world, typically some 2% of the population is pregnant, 1% of the population. But because about 50% are women, that means 2% of women are pregnant at any given time. The number when it comes to the survivors is actually higher. And the reason is that many males were fighting, were at the front. So the results are skewed towards higher number of women. Let me show you what I meant before. There's a difference that was observed between the results from Hiroshima and Nagasaki. On the right, you see incidence of leukemias. Leukemias peak some 3-4 years after the exposure. So that could be observed sooner than other effects. And you see the data for Hiroshima are clearly higher. The other data on the left are for chromosomal aberrations, which assume different forms. And it's a field that was developed after the detonations without entering into the field of biodosimetry. When we don't have measurements, something we can do is take a blood sample from an individual and look at what's called peripheral lymphocytes. So lymphatic cells are mainly in our lymph nodes, but some of them are actually circulating in the bloodstream. These are called peripheral lymphocytes. They don't reproduce. Once they're produced by the bone marrow, they circulate until they die, but it's possible to force them to reproduce. And in that case, if the individual has been exposed to radiation, some specific aberrations develop. They're called dicentrics. You know, chromosomes typically cross at a single centromere. They form this X. Sometimes they have a double centromere. It's called dicentric. When that happens, it's very closely connected to radiation exposure. Unfortunately, it's not a stable aberration. That is, over time, it disappears. So it was not possible to observe it in the survivors of Hiroshima and Nagasaki, but other aberrations that are stable were investigated. They're not as specific to radiation effects, but those people were exposed to radiation, we know for a fact. So there was no confounding factor, and that's what's shown there. And you see the number of aberrations clearly increases with dose. And there is arguably a difference between Hiroshima and Nagasaki. So all this points to what I told you before, yes.
About the cases. And 0.4, we have no cases of leukemias. How is it possible?
These are the inevitable uncertainties, both in the observations, but primarily in the doses. So again, this is not a perfect study. It's far from a perfect study. Yeah. Look at the dispersion, the scatter of the data and the aberrations. It's a huge scatter. So that even more points to the fact that the uncertainties are fairly large. Yeah. So the mechanism of damage, we've ruled out the fact that it's some sort of macroscopic effect, some sort of heating effect. As I told you before, increasing the temperature of, say, water by 1 Celsius requires 4,000 gray. A 4 gray dose to the whole body is lethal. It's the LD 5030. That would only increase the temperature by 1/1000, 1,000th of a Celsius, which is almost impossible to measure. So clearly the effect is to be traced to damage to critical structures, the DNA. I'm sure you'll hear about this again. Data concerning the incidence of the, in particular, cancers has been analyzed with a variety of models. Here are some examples of the models that have been used. The simplest one is the linear model, this one here. As you see, it starts from a point that is not at 0 because that's a natural incidence. So we're looking at data above natural incidence. Linear model. This is linear quadratic. This is pure quadratic. And this is the full model that also includes cell killing. That's because, of course, if the dose is high enough that you kill cells, they will not develop cancer. The cancer induction drops. So these models have been used. And in general, within the uncertainties, and except leukemia, the linear model works fairly decently. in the case of leukemia, if you, well, it says there, you can see it. Data can be fitted within the uncertainties with a linear model, unless you exclude the high dose range, and then you have better fit with the linear quadratic model. But what is the point? The point is that if you try to extrapolate these models to the low doses, you get this. So while the different models may, in principle, match the data acceptably within the uncertainties, if you extrapolate to low doses, they open up horribly. And there's no evidence correlating the models and the data that are available. So again, we only have data for relatively high doses. That is a study that concerns radiotherapy patients and radiation-induced second cancers. This has been done at Columbia University. And you see the only data that we have are for this part here of the doses. Clearly above a dose of 3 gray or so, people died. Nevertheless, these data have provided us with a really, really important piece of information, that is the so-called risk factor. Risk factor is the number of excess cancers, lethal cancers, fatal cancers, induced per sievert, caused by an exposure to one sievert to the whole body. So what's been observed with the survivors is that this risk factor is 10%. But their exposure took place in extraordinary conditions. It's an instantaneous exposure where the dose rate is exorbitant. So the risk factor that we use for radiation protection is half of that. It's 5%. In fact, we use 5% for the population. We use 4% for workers. You may wonder why. Any guesses? 8. Because the age group of the workers in countries that respect laws goes from 18 to 65. And that's a period where our radiation sensitivity stabilizes. Whereas it's known to be higher for children, you see it there. So for children, it's a much higher sensitivity. And therefore, when the population encompasses also all the ages, the factor is higher. We don't have a specific risk factor for infants and children. We know that it's higher. In the United States, they use 10% for the fetus, but again, only in the United States, the NCRP. We go by the recommendations of the ICRP, the International Committee on Radiation Protection. We do know that the elderly are less sensitive. All the processes are slower, including cancer growth. Perhaps it's 2%, but there is no consensus. So this is not part of recommendations and even less of regulations. Concerning studies at very low doses, one can argue that a reasonable estimate of the effects of 1 sievert, 1,000 millisievert, can be derived by the observation of 500 individuals, all identical or similar, meaning with similar living standards, nutrition, place where they live, which means natural background or radiation. You need about 500 individuals, fairly similar. If you want to quantify the effect of 100 millisievert, you'd need 50,000 individuals that are so similar. If you then want to establish the effect of 10 millisievert, which is close to a typical CT scan, full body scan, you'd need millions of individuals. So clearly we don't have this data, we'll never have this data. What is the consequence? That we use a model that's called linear no threshold model by extrapolating linearly from the observed data all the way down to 0. In a way, it is an assumption of ignorance. This is how I like to present it. we recognize that we don't know what happens. So we draw the simplest curve between the known data and zero. And that happens to be a line that goes straight through the origin. There are studies that suggest an over-response to low energy, to low doses, phenomena called genomic instability, bystander effect. I will not discuss them. And other studies that instead suggest that very low doses may actually be beneficial. Now, it is known that exposure to certain chemicals, very low doses of these chemicals may produce some sort of tolerance to them, if not under response to them. A similar effect is postulated by some studies that say, oh, at very low doses, we may actually have negative damage. Negative damage means benefit. It's not proven. There are many, many confounding factors. So what do we know? We know that LET plays a role. We know that higher LET, higher ionization density, increases the probability of double-strand break. Double-strand break is difficult to repair more than single-strand break. Single-strand breaks are repaired within minutes. Double-strand breaks, hours, several hours, more complex. And sometimes our cells guess a sequence. That can be a problem. It has been observed this in cell cultures. Many studies are done in cell cultures. As you can see, low LET radiation corresponds to a higher survival than higher LET radiation. Alpha particles are very high LET. Neutron recoils, particles released by neutrons, also have fairly high LET. They cause more damage. Something that is missing when the LET is very high is the initial plateau. See, at the beginning, for low LET, there is a bit of a plateau. That indicates that those very low doses are fully repaired. Whereas if you have high LET, the drop is immediate. It's an exponential drop, which means that even a single hit, in principle, can cause the consequence. So the mechanism is the one I told you. If you have a single strand break, it gets repaired, the bases are conjugate. If you have single strand breaks far from one another, they also repaired as independent breaks. If the double strand break happens like this, two segments separate, and then it's complicated. Other factors that are known to affect the response of cells, oxygenation. So when cells are well oxygenated, they are typically more sensitive. Here you see curves for low LET radiation, hypoxic cells, low oxygen concentration, high oxygen concentration. So hypoxic cells are less radiation sensitive. This is traced to the fact that especially low LET radiation produces a lot of free radicals in the cytoplasm. Doesn't only hit the DNA, but it mainly interacts with the cytoplasm. So the cytoplasm is the fluid around the DNA. The DNA is only 1% of the volume of the cells. So clearly, most of the interactions will be outside of the DNA. Well, when free radicals are formed, they can diffuse. And in the case of low LET radiation, X-rays, gamma rays, and their electrons, the presence of oxygen enhances the lifetime of the free radicals, which means they have more chances of doing damage. High LET radiation instead acts more directly on the DNA. So the effect of the oxygenation is less pronounced. That's a very important factor. Other important factors, which again you'll hear about in greater detail, the cell cycle. Cycles that undergo division mitosis have phases that are more sensitive than others. The phase called synthesis, where the new DNA strands are created, is less sensitive. When the DNA, the chromosomes are double the amount corresponding to one cell, so they're the amount corresponding to two cells, you're essentially doubling the target. You now have double the DNA, double the target. And not only, the DNA is all clustered. It's a perfect target. It's easier to go through with tracks of the radiation and really wreak havoc on this DNA. So a lot of studies have been done, and it's been proven by these two gentlemen, Véronique Tribondeau, that there are some rules behind the sensitivity of the cells. Cells that reproduce rapidly or frequently, I should say, are more sensitive. Cells that have a long mitotic future. You know, cells know how many events of division preceded them. There's a segment of the chromosomes called telomere that's far away and gets shorter and shorter at each division. So cells, in a way, know how old they are or how old their predecessors are. At the beginning of their mitotic life, they have a long mitotic future, they're more sensitive. And typically cells that are not differentiated, like stem cells, that don't have yet a specific role, function, organ to belong to, are more sensitive. These are some tissues formed of resistant cells, they're resistant themselves, and tissues that are formed of sensitive cells are more radiation sensitive. I do mention a couple of exceptions because one of them in particular we use in dosimetry. And this exception is the peripheral lymphocytes. So I told you before that blood samples can be taken and the lymphocytes may be analyzed. They go against the rule that I've mentioned before. They're very differentiated. They do not divide, and yet they're very radiation sensitive. One of the very first tests that can be done on people exposed to high doses of radiation is just scoring the lymphocytes, counting how many they are. If the number is between, let's say, 1,500 or 2,000 and 2,500 counts per microliter, that's a normal range. As it drops, when it drops rapidly, it's a sign of very severe exposure. So this is a good way to triage patients who've got a very high dose, including those that are hopeless, including those that there's no point in treating, maybe with palliative care, but in terms of optimizing the hospital resources, you want to know that. For those instead that had a lower drop in the lymphocytes, more advanced tests will be done. Tu farai biodosimetria? Verrà fatta la biodosimetria in quello. I was asking whether biodosimetry is planned for the rest of the week, you know? You wouldn't know. Anyway, okay. So more accurate tests that take more time can be done on those that go lower doses. So this is a bit of a premise to what I'm discussing now, that is radiation protection and how we do it in practice. That is by developing techniques that are dosimetric. First of all, there are two types of effects, deterministic and stochastic. Deterministic effects, we just want to prevent them. We just need to keep the doses below the threshold. They don't happen. Stochastic cannot be prevented, but we can try to minimize them, reducing their probability to an acceptable level. So that's the goal. Let me go quickly through this and let me get to this one. The quantity that we use is derived from the quantity that we've introduced. That was absorbed dose. This is the absorbed dose to a specific tissue due to a specific type of radiation. So what we do is we go from the absorbed dose to something that we call effective dose. And the formula that you see here applies two weights to the absorbed dose. One weight, one factor is due to the radiation type. The other one is due to the tissue type. This first product here, the product of the radiation weighting factor and the dose, is called equivalent dose. The double summation is called effective dose. It's a sum over all the tissues and all the radiation types. What does it mean? It means that you can define this quantity even if you radiate, I don't know, 1 foot of your body, and just that. You just need to know which part of the body was exposed, the dose to that part, and the type of radiation. And then you can come up with this effective dose. And why is effective dose important? because cancer incidence is proportional to effective dose in the linear no threshold model. So we assume that there is a direct proportionality between this quantity effective dose and the risk. So what are these weighting factors? Let's look at the radiation weighting factors. Many studies have been done examining for different values of LET, that linear energy transfer that we've mentioned, which is the ionization density. Many studies have been done on the biological effectiveness, and everything has been compared to a reference radiation that is X-rays, 250 kilovolts. What you see here is that for all the biological models that have been examined, it's a very simple message. For all the biological models, pretty much all of them, we've observed a maximum in the damage around 100 keV per micron. And after that, in cells similar to ours, we've seen a decrease in the effectiveness. A decrease doesn't mean that radiation of a higher LET doesn't cause problems. It means that we're wasting radiation. It's as if you were shooting somebody 10 times in the head. You just need to shoot that person once, I guess, in the head. The other 9 bullets are wasted. So in terms of effectiveness, it goes down. It's what biologists call overkill. You overkill the cell, okay? So let's see some of the weighting factors. These are the weighting factors for different types of radiations. As you can see, X-rays, gamma rays, electrons all get the same. It doesn't surprise you because X-rays release electrons. So we're really just looking at electrons in all cases. Factor is 1. Neutrons have factors that depend on their energy. Protons are given a factor of 2. Alpha particles, 20. Let me show you another model that my group studies. So we work with zebrafish. We work with peripheral lymphocytes. We do biodosimetry with those. We also work with the vegetable model, a so-called vegetable biota, a living entity that is not of animal origin. It's the common onion. It takes the Latin name Allium cepa, it's the common onion. It's a very well-known model to study chemical toxicity. We use it to look at radiation effects. And what we look at are these little formations here that appear when cells divide. When an onion develops from a seed, the roots grow very quickly. If you expose the roots to radiation, they may develop these structures called micronuclei. It's nuclear material, fragments of chromosomes or full chromosomes, and their number can be correlated to the exposure. Now, let me show you something. Here is the number of micronuclei as a function of dose for X-rays. And here it is as a function of dose for alpha particles. The ratio between the two slopes is about 20, which is the ratio recommended here. So this model is very, very promising. This is something we're investigating. It's one of those topics that, should you be interested, is open for thesis work. We have a lot of experiments going on. We're looking at a variety of toxic agents. Also, as we give very high doses, we see the peak and then the decrease. And now you remember, I've introduced this model of effects with cell killing. This is most likely what happens. So that's the tissue weighting factor that I was discussing. And now let's look at the radiation weighting factor. Now, tissue weighting factor. The tissue weighting factor indicates how different tissues are prone or susceptible to developing fatal cancer. Fatal cancer, what do you think it depends on? When is it that a cancer may be fatal? Yeah, and when it's not easy to diagnose, when it's not easy to treat. So the lethality of a cancer doesn't only depend on biology, it also depends on medicine. In fact, looked at the tissue weighting factors recommended in 1991 and those that are recommended now. Our biology hasn't changed in 30 years. It takes centuries and centuries for our biology, in fact, more than that, for our biology to change. The reason these factors have been modified is that our knowledge, our medicine, our diagnosis has changed. So let's look at some key differences. This is supposed to be an arrow. Sorry, it didn't come out well. There you see the female breast. In 1991, it was given a weighting factor of 0.05, which is quite low. At the time, recognition of the severity, seriousness of breast cancer wasn't there. It also wasn't receiving a lot of attention. In a, I'll say it, male-dominated world, there was a lot more interest in gonadal cancer. And gonads, testicles, were given a weighting factor of 0.2. Very high, the only tissue that was getting this value. We now know that testicular cancer is treatable, is easier to diagnose because it's an external organ. People have gone on to win 5 Tour de France having had testicular cancer. You know the gentleman named Lance Armstrong. Of course, afterwards, he was taken away all those titles because he was like a bionic man after all the treatments he had received. But again, so the gonads nowadays receive 0.08, down from 0.2. Breast is up to 0.12, which is the highest value that is used now. And you see the other organs or tissues that receive a high value. They are those that we mentioned at the beginning. Remember the GI tract, the respiratory tract. We said that they are the tissues that undergo mitosis all the time. And also the bone marrow. They get the highest weighting factor for tissues. They're the most sensitive and sometimes the most difficult to diagnose and treat. So how we have how do we manage this radiation protection and the goals in particular? We have some so-called cardinal principles that apply. There are 3 cardinal principles. Anything that uses radiation has to be justified, it has to be optimized, and in some cases, limits to the dose apply. Justification means you use activity if there's a net benefit. You use, radiation if there's a net benefit. You use radiation if there's no alternative. If you have an MR unit, you can do MRI, and you have it available, and it gives you the information you want without doing a CT scan that uses X-rays, you will do MRI. If there is a pathology that can be treated with high-intensity focused ultrasound, which is increasingly adopted, you'll use it rather than radiation. But if you don't have it available, and what you have is an old X-ray machine, and you're in the middle of a place that has nothing else, you must use it. So again, it's always a matter of using the available resources, the best available resources. Optimization means that you should always try and reduce the doses to the minimum that achieves the goal on hand. So it's what is called the Lara principle, as low as reasonably achievable. You see that. And again, you have to account for the fact that sometimes reducing doses is very expensive. So you have to strike a balance also at the level of society or whether it makes sense to reduce doses to very, very low levels. Might be very expensive. This is how LARA is implemented. And finally, we have the limitation principle. So limitation means that for certain categories, certain levels of dose must not be exceeded. Let's put it differently. Except for patients in medicine, we limit the doses. We don't limit the doses given to patients. You will never interrupt a course of radiotherapy or a CT scan because you've exceeded some dose level. You've completed the work. If you don't complete it, it's actually worse. But for the other categories, for the workers, for the population, we have limits. So how do we establish the limits? we have to look at some levels of risk that are acceptable. Well, there are some levels of risk that are acceptable because there are jobs, occupations, industries that we consider safe. The mean fatal accident rates in what's called safe industries is in the order of 1 in 10,000 workers per year. 1 in 10,000 workers. We hear about accidents on the job all the time. If you look at the numbers, they add up to several units per 10,000 per year. You follow me? So those are acceptable rates. People, unemployed individuals, will not think, I will not take a job as a bus driver because bus drivers die in excess of 5 per 10,000 per year. They will not. They'll think, I got a job. I'm happy. I'm lucky to have a job. I'll be careful. That's what they think. But there are risks. So those risks are accepted in our society. So what we do is we choose limits, those limits, and I'll stop at this. We choose those limits such that those risks or those fatal accident rates are not exceeded. And pay attention. These are observed numbers, frequencies. What we compare to them are risks, which are not observed. They're based on a very conservative model. So they're very, very cautious estimates. That is the framework. So it's a framework where protection is really the key word. Would you like a first break and then we start with the next completely, well, not completely different, but different topic, which is radiation detectors? Yeah. Any comments, questions, doubts? Nope. Okay. It's implemented by the ICRU and we follow ICRU recommendations. Yep. Sì.
Perché diciamo del settore industriale
Ci sono i dati.
è correlato diciamo delle radiazioni o è generico?
No,
Cioè,
no.
qualsiasi tipologia di morte
Non
correlata
sono le attività
al lavoro.
che non includono radiazioni.
Includono, ok.
Cioè,
Quindi-
quello che si fa è dire, ok, queste attività sono accettabili.
Ok,
La gente lavora in negozio, la gente lavora,
perfetto.
fa l'insegnante,
Certo,
eccetera, ma anche
certo.
questo comporta dei rischi. No?
Certo.
C'è un certo numero di morti per anno che vengono espressi in termini di morti per 10.000 lavoratori.
Ok.
E i numeri sono nell'ordine di 3, 4, 5.
Ok.
Una professione pericolosissima, per esempio, settore costruzione.
Sì.
Un'altra pericolosissima, l'agricoltura.
Mhm.
La quantità di trattori che si ribalta, di macchine trebbiatrici che ingoiano le
Certo.
persone, mostruosa, mostruosa. E allora si impongono dei limiti, sì, in modo che il rischio stimato sia molto inferiore alla frequenza osservata.
Io invece, professore, le volevo chiedere questa cosa di cui ne parlavamo prima, forse non mi sono spiegato bene. Quello che volevo dire è che, cioè, è chiaro, il principio del dualismo onda particella è una cosa ovviamente assodata, è chiaro. Infatti è proprio su questo che si basa la mia più che domanda, è una curiosità, insomma. Cioè, come faccio io a dire che prima di un certo momento è un'onda e dopo un certo momento si trasforma in due particelle distinte?
Due particelle distinte. La questione è un'altra. Una qualsiasi entità puoi pensare che oscilli tra stato ondulatorio e stato particellare, perché c'è anche un principio di indeterminazione, per
Certo.
cui tu nel momento in cui vai, tocchi, verifichi cos'è, l'hai alterata. L'hai alterata e quindi se conosci una... Chiaro?
Sì, certo.
Questo in generale. Per quanto riguarda quello che dici tu hai un fotone perché l'hai prodotto in qualche modo e a un certo punto ti appaiono i due elettroni, li osservi.
Ok, quindi
Sì,
una volta che ho
capito?
osservato
Sì.
cioè il dualismo è perso e l'indeterminazione è persa. Ok,
Sì.
in
Qui
questo senso.
compaiono i due elettroni
Certo, ok.
e ci sono rivelatori, e ora di nuovo questo materiale lo potrei documentare tutto, ma
Sì, no, vabbè, insomma.
rivelatori che ti fanno vedere all'improvviso la comparsa di due traffici, che è degli elettroni, negatrone e positrone, che in un campo magnetico vanno in direzione opposta e che perdendo energia descrivono una spirale, che sono bellissime tra l'altro, ma di nuovo
Quindi sì, insomma,
ho dovuto fare una
il
scelta.
concetto è questo, è che dopo l'osservazione si perde l'indeterminazione.
Esattamente. Ormai hai le particelle.
Certo,
Ci sono le
chiaro,
particelle.
chiaro.
La conversione è avvenuta.
Sì,
Anche legata alla ricchezza d'onda, può essere o meno assorbita in una salina di concetto all'interno cioè, se non vedo una lunghezza d'onda non me la sorbe.
Allora, nel caso particolare citato da lui, cioè la produzione di coppie, occorre che la lunghezza d'onda sia inferiore a un certo valore, cioè che l'energia sia superiore a un certo valore, il quale valore spesso in electron volt è
20 mega.
un mega electron volt punto 022, che è pari a 2 volte la massa a riposo di un elettrone. Volentieri.
Sta qui glielo
Non è che poi dopo appaio un abusatore. No, anche perché io vivo perché esistono i miei studenti, per cui per me voi siete una specie protetta, no? Dico sul serio, eh? Io vivo la mia professione come un qualcosa.
Ma lo si nota, si nota tantissimo.
Ok.
E se no, anzi, ne approfitto per iniziare il discorso. Io, per quanto possa contare, le faccio i miei complimenti perché è una lezione interessantissima, chiarissima, di cose che io.
Ma ora divento tutto rosso.
No, ma no, ne è vero.
Lo prendo volentieri. Lo prenderei macchiato se non è chiedere troppo.
Io che non riesco a stare fino alle 6 per impegni, quindi volevo già salutarti.
Non
Quando
per-
poi andrò via per le 5, magari questa lezione non.
Io non so fino a che ore resisteranno tutti gli altri,
No,
vediamo un attimo.
secondo me resisteremo proprio fino alla fine perché è una lezione veramente, almeno per me, però io sono del campo, quindi ma è una lezione veramente interessante.
Allora,
Ci tenevo a salutarti
proprio
prima.
perché sei del campo, la gradisco particolarmente questa tua opinione.
No, ma assolutamente, perché hai fatto proprio una carrellata di tutti.
È quello che provate a fare, visto che poi avete il resto della settimana
Assolutamente,
dove certi aspetti saranno sviluppati in dettaglio. Ho pensato di toccare un po' di tutto, spero che non sia di non perdervi per strada, ma ho cercato di dare un filo logico a tutto.
No, devo dire, alcuni concetti devo pure riprendere, però sono molto, molto chiaro.
Ringrazio. Va bene.
Alcune cose devo approfondire.
Bene.
Non so del campo, però. Per esempio, l'ultima slide che hai mostrato, quindi 10 alla meno 4, questo in effetti è l'osservato.
Queste sono frequenze
Perché
osservate.
poi alla fine la soglia, quello sui limiti, è stato messo su 1 su 1000, ce la fa, sul contrario. Perché
Sì.
è stato partendo dal 5%
Esattamente.
di Sievert, poi i 20
Esattamente.
di.
Usi il fattore di rischio, usi un rischio accettabile e dici, ok, cosa mi dà un rischio pari a circa 10 alla meno 4? E al ritroso trovi la dose, che è il limite per la popolazione. È così, esattamente così. E è bella, come logica, è una logica, molto stringente e molto protettiva, perché confronti un rischio a un'osservazione. Capisci? Già il fatto stesso che uno è potenziale è un rischio e l'altro è un'osservazione, sono frequenze documentate, significa che stai dal lato della cautela.
Anche perché quello poi 10 alla meno 4, forse la popolazione è anche un po' di meno, però è il limite. Questo invece è osservato. Quindi ecco perché le radiazioni a lungo andare sulle attività sono anche meno rischiose.
Esattamente così. Esattamente così. È tutto chiaro lassù? Abbastanza? Mi raccomando, interrompete se ci sono domande, perché è per voi.
Ecco.
Grazie mille.
Io zucchero ho lasciato quello di default.
Ok. Allora non lo giro perché quando lo macchio mi
Esatto.
basta. Perfetto. Gentilissimo davvero.
Ah, perché-
Cosa ti ha portato a fare questo programma?
ma io sto facendo per piacere queste cose.
Ma poi il primo livello lo prendi con quale prospettiva?
Io sono stato assunto per prendere per il secondo. Io c'ho...
Allora lo frainteso quello che stai per fare.
Ah no, sì. Allora, no. Io...
Ah, tu parli a livello del master, noi parlavo dell'esperto di realizzazione.
No, secondo livello mi piacerebbe prenderlo, ma come dire, io solitamente faccio consulenza, faccio concertazione, così, non c'è e questo possibilità di avere pensando sempre come gestire il rischio prima azienda capitale e questo potrebbe per parte e parallelamente ho iniziato anche, ho fatto l'anno scorso, stato sulla preparazione, per fare attività tipiche rispetto alle città, quindi rispetto ai dentisti, perché effettivamente il mercato enorme, i tecnici ce ne sono tutti e le parcelle sono
Come no?
paragonate a quello che uno fa, nel senso in termini come razzotti dentici. Poi vabbè, io non amo il calcio, perché scende da un figlio che non obbliga a giocare, quindi spende il tempo in calcio attività.
Capito.
No,
Come va? Bene, bene, bene. Mi sto sfinendo. Un po' sì, dai.
Però il problema è che quando uno poi affronta la simmetria con i livelli di rischio, diciamo, è la base del mestiere, diciamo, sono concetti che per chi non ha mai fatto, capisco, diciamo, che risulta impegnativo come argomento.
Spero di riuscire a dare un po' di basi, perché oltre non si può.
Sì.
no, forse magari chi non è tecnico, cioè ci sono molti tecnici non più educati, perché c'è magari persone che fanno top internazionali, penso che per loro sia difficile. Però
Vedete, non è indispensabile cose da tagliare o semplificare, io li gradisco molto.
Molto da
Questo chiedo, da quanto capisco, forse i problemi con il semplificare, con tutto può essere
ma secondo me non è invece, cioè, nel senso, secondo me sono due target diversi, sono due facce la stessa cosa. Per la gestione di un'emergenza, così dire, ce ne sono in tutti i blocchi.
Sempre io. Questo è il risultato di tanti anni di insegnamento dove io cerco di implementare scontri di tempo. Da qui a dire che sia migliorabile, no, è migliorabile.
No, ma perché anche per dire, anche solo dire che ci sono attività. A questo momento si sente dire di un tecnico che ha vagliato le varie possibilità e ne ha scelto una. Invece magari se non sa che ci sono più possibilità, potrebbe dire no, ma non lo devi rivelare. Cioè, nel senso, diventa più complesso prendere una decisione rapida, insomma, se questi argomenti uno non li ha trattati. Quindi sembra che sempre troppo semplice, scontato, invece non è
gli avvocati si possono legare per stoccarsi il problema è che tu devi stimare i valori delle cose. Cioè, per esempio, io lavoro 100 persone civili. Intanto da noi, ma in uffici regionali sono stati, per esempio, le sicurezza sono stati requisiti indagate perché hanno fatto previsioni sbagliare, che poi sono sbagliare, però la faglia capire la natura probabilistica della presa al magistrato che è quanto mai complesso. Noi abbiamo fatto una campagna anche di comunicazione di auto con i magistrati, facendo venire da noi, cercando di spiegargli che il previsore non sarà bene, che abbia a che fare con dei modelli probabilistici. Ma al mondo della magistratura questo lo viene in realtà avevamo fatto uno studio della misura del radio di dose ambientale, avevamo fatto uno studio di correlazione con gli eventi sismici, ok? No, un articolo, e abbiamo ripetuto 8 volte dicendo che tanto era uno studio rivolto al passato che assolutamente sì, bisognava approfondire il modello, ma parlare di previsione non ci siamo azzardati.
Me lo ricordo che usando la calcolazione modulare,
Quella cosa lì,
Quando è nato il primo grado, quelli dalla commissione grandi rischi, dopo si erano
rimasto del cose diciamo, il Bernardino è stato condannato.
Per ignorato.
Che praticamente il professor Giuliani fece questa cosa basato su una codifica da grandi rischi. Lui ebbe, secondo me, un po' la cosa di andare a fare l'intervista prima della riunione. Poi ci fu il giornalista che disse cosa possono bere un bicchiere di vino, questi figli assolutamente, e poi successe quello che è successo. Poi il verdetto è stato sfondato sul fatto che qualcuno chi è rimasto in casa si era basato sul valore. Era davvero
quello che è passata, secondo me se lo dicono loro al magistrato sembra come la scelta di un magistrato, ma se loro avessero la volontà perché mi pare anche questa cosa
allora il problema è che quando tu fai una previsione hai che fare, cioè il tuo di fronte a vediamo una chiamata Landina
Quanto riguarda assolutamente. Quello che non è mai stato fatto in modo adeguato è una fattura del terreno molto estesa, maglia fitta, perché se sottoterra qua qualche fessura, un punto di frattura si muove, non è assolutamente detto che vada a escarsi, anzi, non esce. Quindi va seguendo un percorso che pare che magari esce a decine di chilometri o più di distanza. Quindi o si ha un qualcosa che consente di mappare tutto, perché io sto sviluppando dei sensori molto piccoli in rete che comunicano con protocolli che non usano satelliti e simili, proprio per vedere se nella zona della Garfagnana, che è abbastanza attiva, vediamo. Noi abbiamo una stazione bellissima, misura le acque profonde, vede se c'è radon, misura l'anidride carbonica, il pH, ma è un singolo punto. Il singolo punto non risponderà mai alla domanda, non risponderà mai. Quindi o si copre il territorio con maglie sempre più fine e a quel punto si vede se c'è un qualcosa, ma non si può dire sta per avvenire sotto l'Aquila o quel che sia, no, non si può. Anche perché all'epoca Giuliani disse
sul Mono e avrebbe spostato tutti all'Aquila. Era quello il problema, ricordo.
Ok. Okay, so let's start looking at the tools that we have at our disposal, so that we can try to measure some of these quantities and derive the information that is of interest to us. we need radiation detectors in the first place. So how are these detectors designed? What do they do? Here's the first question. We can classify the detectors based on their structure. Some detectors, I've already mentioned it, are filled with gas. Others are solid state devices. Some of them are materials that emit light when exposed to radiation. They're called scintillators. Other solid state devices are based on semiconductors. We even have liquid phase detectors, liquid scintillators, liquid ion chambers, superheated emulsions. That's what I developed myself. These are all liquid phase detectors. So one possible classification is based on the structure. Another classification is based on the information that they provide, their output. The simplest ones simply produce counts, clicks, when exposed to radiation. If these counts are very frequent, we're getting closer to a source. If the counts are lower, we're getting farther away. But sometimes it's all we need. Other detectors tell us how much energy has been deposited or is being deposited in something that is similar to tissue. These are dosimeters. So they give us is an integrated quantity. They say, if you stand there for this long, you'll get this dose. In some cases, it's somewhat easier. In some cases, it's very complicated. I'll show you examples. And finally, there are detectors that give us information on the radiation field. They tell us not only what radiation type we're looking at, but the energy. So they're called spectrometers. For example, scintillators, some simple ones based on sodium iodide, belong to this category. Let's see some dosimeters, just to give you an idea. Remember, we mentioned the air as a material that having an atomic number, an effective atomic number, similar to soft tissue, can be used to measure the energy deposited in tissue. So simple chambers like this one, this is an ion chamber, where we measure the ionization that occurs inside, can give us information in their respects. We can even use materials that have nothing to do with our body. Before we talked about thermoluminescent materials, those ceramics that in Japan have been used to reconstruct the doses. That's called retrospective dosimetry, by the way. You look back and try to understand which dose. So this is a crystal of lithium fluoride. We don't have lithium inside. We don't have fluorine inside. But since we've done it together before, what is the effective atomic number of this compound, in your opinion? So we have lithium. Lithium was which atomic number? See, I told you we were going to need it. Lithium is 3. Okay. And fluorine? 9. Fluorine is 9. So what do we think of the effective atomic number? Where will it be, roughly? 6. Well, but let's think about it. What was water? Yeah, water was 7.4. Air was 7.6. So the number is always closer to the higher atomic number of the two. So fluorine is 9. Most likely the number will be between 8 and 9. It's 8.2. But 8.2 is not far from 7.5. That is the number for tissue. So although this material is not at all formed by metabolic elements, we don't have them inside, its behavior when it comes to photons, to photon interactions, is going to be similar to that of tissue. Of course, we will have to correlate its signal to the dose, but we can expect the interactions between photons of different energies to happen in lithium fluoride in a way similar compared to tissue. You follow? So that helps. This is to remind you, there's no lithium fluoride here, but this is to remind you of the effective atomic numbers for those materials. And this is also to remind you of that very important graph with the line corresponding to soft tissue. Okay, Now, completely different story applies to neutrons. I love neutrons. I have been a neutron dosimetry, I don't want to say expert, but researcher and a neutron spectrometry researcher for many, many years. It's one of the most challenging types of radiation. When it comes to doing dosimetry of neutrons, we want a response that is very complicated. It's this one here. We want a response that is relatively low and relatively flat for low energies. That for neutrons of around 10 keV and up to 1 MeV, we want a ramp in the response. We want it to go up by a factor of about 40. And then we want a new plateau. Then it gets even more complicated, but that's for very, very high energies. Now, what you see here is a spectrum which you may encounter around a nuclear reactor, a nuclear power plant. Around the nuclear reactor, and there's great interest in Italy now as we talk again about the possibility of restarting with nuclear power production. There's a great interest in reacquiring our knowledge of how to do neutron measurements, neutron dosimetry, neutron spectrometry. So today I'm here with you, but in principle, I'm opening a school in Pisa. Of course, I had to miss the first day. That goes on tomorrow and then the following day when we talk about modular nuclear reactors and the safety and radio protection and security issues correlated to them. So tonight I have to drive back to Pisa and I'm the first one that lectures tomorrow morning. Just to tell you how much I care about you guys, because really, this is not the ideal day for me to be here. Anyway, the point is, a typical spectrum of neutrons around a nuclear reactor looks like this. There's a first peak that is due to the fission neutrons. So when you split a uranium nucleus, you also release neutrons. 3, 4 per fission event. Those neutrons come out really fast. They have a most probable energy of about 2 MeV, quite high. Those neutrons inside the reactor quickly slow down, as we say, that is, they lose energy. They scatter in the materials, they lose energy, and finally they become thermalized. Remember, we talked about thermal energies, and we said that the energy of a molecule at room temperature has a certain value. Well, thermal neutrons have a different value. But again, it's the same concept. They are in equilibrium, in thermal equilibrium with their environment. Molecules, room temperature 0.04 electron volts, neutrons 25 milli electron volts, typical mean energy of the thermal peak. So neutrons start fast, they're born fast, they slow down, and then they accumulate in the thermal peak. You may wonder, well, why doesn't the thermal peak keep on growing? Because those neutrons are either absorbed or they cause more fission. So there is an equilibrium that gets established. The point is that we need to apply a weight to these neutrons based on this ideal response function. The mathematical operation is a convolution. That is, if you do the convolution of the spectrum over the ideal response, you get a new spectrum. And now the fast neutrons, as you can see, appear to have a much higher peak because their damaging action is much more pronounced. These are much more damaging than these neutrons here. So to measure neutrons, to measure their doses accurately, we need something like this. And getting something like this is super complicated. Let me show you some solutions that are used. This is a so-called epitaxial semiconductor. A semiconductor whose surface can be interrogated in different regions. Above this semiconductor, we put different materials that respond to neutrons of different energies, respond to fast neutrons via polyethylene, respond to thermal neutrons by a boron layer. And then we get the combination of responses that gives us something close to this. Complicated. That's to give you the complicated part. But let's start from the basics. So let's define a key quantity, detector efficiency. The efficiency of the detector is simply the number of counts that it gives you compared to the number of rays that are emitted. Nothing simpler than that. You have a source, it emits a certain number of rays. I don't know, help me count them. 3, 4, 5, 6, 7, 8, 9, 10, 13. I'm lost. 15, 3 more. They're about 18, is that correct? So let's suppose they are about 18. As you can see, only 3 of them enter that detector on the right. That doesn't mean that they're all detected. In fact, you see one of them actually goes through the detector. Only 2 stop in the detector. So detector efficiency in this case would be 2 out of 18. That's the detection efficiency. Number detected over the number emitted. But we can multiply and divide by the same number. Nothing changes. So let's multiply and divide by the number of rays that reach the detector. How many rays reach the detector? 3, because now we also have to count the one that goes through. So 3 reach the detector. Let's divide the number that reaches the detector by the number emitted. 3 over 18. That is strictly a geometric factor. It depends on how big the face of your detector is compared to the full space into which radiation is emitted. That is 4 pi. Let's call that geometric efficiency. Now we have to look at the other ratio that we have. That was number detected. Now we have to divide by number reaching the detector. So those reaching the detector are 3, those detected are 2. So we have an efficiency that is 2 over 3. That's an intrinsic property of the detector. We call that intrinsic efficiency. So the key components to the efficiency of a system or the sensitivity are its geometry and its intrinsic properties. We can define a geometric efficiency and an intrinsic efficiency, starting from the very simple definition that I gave you, which is number detected over number emitted. Okay? How can we affect the geometric efficiency? Well, we make the detector bigger. Now we're covering more of the space into which radiation is emitted. How can we change the intrinsic efficiency? Well, we can make the detector thicker or change the material. We use a material that has more interactions, maybe higher density, a higher atomic number if we're looking at photons. If we're looking at the radiations that we're mainly concerned with, that is gamma rays or neutrons, as I told you, we have an exponential attenuation. So we have a probability of transmission of photons, that is 1, probability of transmission of neutrons, that is this one. See, neutrons and photons don't have much of a choice. When they enter the detector, they either interact or not, period. They don't have a lot of choices. They either go through or interact. We have the probability of transmission, this one here. So 1 minus that is the probability of interaction, very simple. This is the probability of non-interaction. So 1 minus that is the probability of interaction, intrinsic efficiency. And we can play with 2 pieces, the material, that would be mu or sigma, and the thickness, that is x. We can make it thicker or thinner, and we can change the material. In principle, this should be a different blue level, but they look all very similar to me. Sorry about that. So geometric efficiency, intrinsic efficiency, okay? All right, question for you. Let's look at these 3 cases. In your opinion, assuming that in all cases the detector is made of the same material, assuming that the source is the same, which one is more efficient? Would you say it's the most efficient, or would you say it has the highest type of efficiency? What kind of efficiency? It has definitely the highest geometric efficiency. See, the source is almost surrounded by the detector. So all the rays, except for those going up, all the rays cross the detector. But we don't know whether that material is efficient at stopping those rays. See, the thickness of the material in this case is much lower than the thickness in this case. So if the material has a very high density, a very high atomic number, or whatever makes it interact with the radiation of interest, then it's possible that even a thinner detector will interact with all the rays, but we don't know at the beginning. The only thing that we know for sure is that this has the highest geometric efficiency. And between these two, which one has a higher efficiency? This one. This one has a higher efficiency compared. See, the detector is identical. The source is the same, but it's closer. So what do you think is the geometric efficiency in this case? Exactly. Half of the radiation emitted by this source enters the detector. Half goes in the opposite direction. That's a 50% geometric efficiency. That clear? So this is how you analyze. I'm making it simple, okay? This is how you analyze detectors. You have to account for intrinsic properties and geometric properties. All right, let's have a look at gas field detectors. The simplest case, we have a volume of a gas, air, for example, and we have two electrodes, positive one anode and negative one. When radiation produces charges, ionizations, you'll have the negative charges travel towards the anode and the positive charges travel towards the cathode. You can collect the signal in different ways. For example, you can record the current going through these two electrodes, between these two electrodes. So typically you'll have a power supply, a battery. You'll have a meter, for example, an ammeter that measures current. That's one way to do it. So let's suppose that we're exposing this detector to a flow of radiation, a constant flow of radiation. And let's suppose that we apply a difference of potential between these two electrodes. At the beginning, the difference of potential will be, for example, very small, very low. We are producing ions. We need to attract them to the electrodes. But you see, you have a lot of negative and positive ions near one another. What is it that they tend to do? They tend to recombine. So if the difference of potential that you apply is not high enough, you will lose some of those ions. They will recombine. So if you irradiate uniformly the detector, you will get a maximum reading only if the voltage is high enough. And then you'll be operating your system in so-called ion chamber mode or ionization chamber mode. It's a very simple device. It's a very useful device. If you fill it with air, we said that it can measure something similar to the dose in tissue. Remember, because air and tissue have similar effective atomic number. If you look at the X-rays, of course. So here comes some really old-fashioned devices. They look like guns from some old science fiction movie, but they're really ion chambers. And these are used by radiation safety officers to monitor the exposure levels in beams of X-rays used in medicine or to monitor environments. Let me tell you something interesting. We said that patients are not subjected to dose limits. Remember, they get the dose that they need to get for the procedure, CT, radiation therapy, whatever. But before entering the room where they receive the procedure, they're members of the public. They're not yet patients. So suppose this is the waiting room and there's some X-ray machine in the other room. As long as you're here, your exposure has to be monitored. And it must be ensured that you don't exceed those limits, the dose limits that apply to you as members of the public. And that dose limit is 1 millisievert per year. So one can do the math and say, okay, how many weeks does a person work on average per year? Let's say 50. how many hours does a person work per week? Let's say, and now it's less, 40. So 40 times 50 is roughly 2,000. So you have to make sure that the dose they get per hour, I'm just giving you an example of how this is done, okay? So 1 millisievert divided by 2,000 hours is the dose rate that must not be exceeded, that somebody will check with a device like that. So the radiation safety officer will go into the waiting room and will make sure that the dose rate is below 1 millisievert divided by 2,000. That's the dose rate per hour. And why is that? Well, because it's possible that somebody will go to the waiting room every day of the year, for example, accompanying people. You know, there are people who do that. There are people who walk dogs, right? There are people who walk patients and wait for them. So they may go and spend every day of the week, 8 hours a day, 5 days a week in the waiting room. We need to make sure that they're not radiation workers. So they have a limit that is 1 millisievert per year. So we have to make sure that they don't exceed that limit. Do you understand? So this is how you would do that monitoring. The moment the person enters the room where the procedure is done, the limits do not apply anymore. Is it clear? It's a somewhat strange setup, but that's how it works. Okay, so X-rays. We were talking about X-rays. X-rays are produced, I mentioned it before, by sending electrons against a target. We produce electrons with a filament, thermionic effect. They're released. There's a lot of current going through the filament. Then we apply a difference of potential. They strike a target, typically tungsten. You're all very young, but I'm sure you've seen incandescent light bulbs, not just LEDs or the fluorescent light bulbs, okay? So incandescent light bulbs, the ones that become really, really hot, they have a tungsten filament. Tungsten is used because it has a very, very high melting point, some 3,500 Celsius. So here, when you're hitting the target with a lot of electrons, the target gets really, really hot. You need a material that can tolerate that heat and dissipate the heat. That's why tungsten is used. When you do that, you get X-rays through the two mechanisms that we mentioned at the beginning, characteristic X-rays and those that come from electrons changing their path. That's called Röntgenstrahlung. Röntgenstrahlung has this spectrum here, and the characteristic X-rays have produced these lines here. We say that a spectrum like this has an effective energy of, compared to the maximum that is here, compared to something like 45%. Let's keep that in mind, 45% of the maximum. Let me tell you why I want you to keep that number in mind. Let's suppose that we make X-rays at these different potentials, 100 kilovolt, 200 kilovolt, 1000 kilovolt. The effective energies, therefore, will be 45% of those values, these values here. What are those X-rays going to do in air? The low energy X-rays will produce some photoelectric effect in air. Not much, 10%. The rest, 90%, will be quantum. Photoelectric and quantum. See, photoelectric effect transfers a lot of energy to the air because it's absorbed entirely, the photon. So the electrons produced have a long range, 12 centimeters. Compton is not very good instead at those low energies. So the Compton electrons only get a short range, 0.5 centimeters. So if we build a chamber like this and we expose it to X-rays, you see we'll be collecting signal from this region here. Can you follow me? Okay. We will be getting signal from the electrons that are in here. Some of those electrons are produced inside, but then they exit. So we lose some of their signal. Some others, however, are produced outside, but their tail goes inside. If we have equilibrium between these two situations, we are measuring correctly the effect of all the electrons. Is that clear? We have a charge-particle equilibrium, as it's called, because what we're losing on one side, we're regaining from the other side. Charge-particle equilibrium. Let's see what happens if we increase the energy of the photons. At 200 kilovolts, the effective energy will be roughly 90. This is an approximation, just for our discussion. You see, the photoelectrons would have a very long range. Very long, they get a lot of energy, but they're very, very few at this point. We mainly have Compton. They still don't have a long range because Compton is not very effective at transferring energy. But if we now go to 1000 kilovolt, that is 450 keV mean energy, now the photoelectrons would have, if they existed, a huge range, but they're virtually zero. Compton also has now a very long range. It's 100%, because Compton transfers energy very effectively at high energies. This is what happens in a patient in radiotherapy. We have Compton, and Compton transfers energy to the electrons effectively, and it's the electrons that kill cancer. Is that clear? So Compton, which is not good at low energies, becomes very good at high energies. But what else are being told here? We're being told that in order to have, and this is the last point of this slide, it's important, that in order to have the charge-particle equilibrium, also for these very high energies, we will need a huge chamber, huge, with 4 meters of volume. We can't do that. That's not a portable device. There are laboratories that have these huge devices, but it's not a portable device. But we can do something smart. Instead of having an air buffer volume around the sensitive chamber, we can put a layer of something similar to air, but solid. Now, the density is going to be 1,000 times higher, and that's going to have the same effects as this volume of air. So if we want to use our ion chamber, I'm coming to the conclusion. Don't fall. Okay. If we want to use an ion chamber for high energy photons, we need to put something around it. It's called buildup, like this thing here. And then it will be able to measure under charge particle equilibrium also those high energy photons. Is this concept clear? It's one of the key concepts of radiation dosimetry. Getting an equilibrium situation between the sensitive volume and the surrounding materials. Okay. Let me show you some simple examples of similar devices. This is called pen or pocket dosimeter. This is a device that it's actually very smart the way it's designed. It's an ion chamber, but it doesn't have any active electronics. It has some quartz filaments. Initially, they get charged positively. These two filaments can move. If you charge them both positively, what do? They separate. Yeah. Now, suppose they're in a volume of air and you have ionization. Progressively, their charge will be neutralized, so they get closer and closer. Suppose one of them is in front of a grid, like this. As they get discharged, because they got more dose, one of them moves in front of the grid and tells you how much dose you received. It's one of the simplest devices. It's passive. So you use it, you read it against the light. It's like a little telescope or kaleidoscope. You look against the light and you'll see that the indicator has moved. And when it's fully discharged, you just connect it to a source of supply and you recharge it. This is one of the very first devices that could be used to monitor exposure pretty much in real time, but without complicated electronics. Pocket dosimeter, pocket ion chamber. This is the response as a function of energy. It should be very flat. It isn't. Let's not discuss that. So this is an integrating device. Then we have the current mode. We've discussed it. Well, sometimes we want to do something else. we want to measure for each event, how much radiation it deposits. So we want to measure pulses for each ray. We cannot do it in this mode because each pulse is very, very small in ion chamber mode. That's why we need to work in integrating or current mode. But if we apply a higher difference of potential, then we start producing pulses that are much bigger. I don't want to do all the mathematics of the pulse generation. The point is, by applying a greater voltage and using a cylindrical geometry, we can get large pulses. And that allows us to see one by one the energy deposited by, for example, gamma rays. I'll skip that part. Let's suppose we keep on increasing the voltage even more. We reach this region here. You see here you had pulses from alpha particles bigger than pulses from beta particles. Doesn't surprise you, the alpha particles deposit more concentrated energy. No surprise there. But see what happens when we're up here? The pulses from alphas and betas are the same. That is the Geiger counter. A Geiger counter gives you counts, but it doesn't tell you if you're looking at alphas or betas, all the pulses are the same. The voltage is very high. The device is relatively simple. It's got a flat response for any voltage here. So you don't need to have very accurate voltage control, which you need here. And it gives you counts. So proportional counter, again, I go quickly through it. We get the pulses. They tell you how much energy is deposited in them. One example is this device here. This is a device that works to measure neutrons. Let me tell you about this. This is important. So here we have a proportional counter, works at high voltage. And we have a gas that responds to very slow neutrons. So it will not be able to measure very fast neutrons. So what we do is we surround it with some material that converts fast neutrons into slow neutrons, a material that slows them down, typically containing hydrogen. Sometimes you see something like this. The neutron doesn't really stop and go into the volume. Sometimes we get lucky, and this is what happens. The neutron slows down, it interacts with the material, it produces signal. Other times, we may get something like this. The neutron goes back. Or the neutron gets nowhere, gets absorbed in the material. So again, without going into the details, we can use those devices working in pulse mode to measure neutrons. Let's move on to the Geiger counters. I told you that the devices respond independently of the type of radiation. Why is that? It's because we allow the signal produced by radiation to become an avalanche, as it's called. It's late in the day, it's a lot of technicalities. I will not go through the details, but the point is, this device, no matter what starts the sequence of these avalanches, works by producing pulses from a complete single avalanche or combination of avalanches, sorry, around the anode. So again, all the pulses are the same. You might think that this device is not very versatile, that it doesn't allow you to detect different things. Not so. If you know how to use it, you can tell, for example, if somebody has been exposed to neutrons. Just to go back to my favorite particle. If we are exposed to neutrons, something in our blood becomes radioactive. That something is sodium. You know, we have sodium in the blood. We try not to have too much because it increases our blood pressure, but we have sodium. When exposed to neutrons, sodium becomes radioactive. If you put a Geiger counter in front of your abdomen after neutron exposure, you'll get counts. And the correlation between the counts and the neutron dose is known. So we can use a Geiger counter for that purpose. I invite you to visit this website and play with the simulation of a Geiger counter. You will see how the Geiger counter works when you put different sources in front of it and when you put different materials. You'll get the class. And when you put different materials between the Geiger counter and the source. Let's think about this together, and then we take a break. Suppose your source is gamma rays. What happens if you put increasing thicknesses of a material between the source and the detector? How does your signal change? Yes, but how do the counts decrease? Exponentially with the thickness of material. So you put increasing thicknesses of material, your counts decrease as an exponential. If your source is high energy gamma rays, your exponential will drop less than if it's low energy gamma rays, because low energy gamma rays are easier to attenuate. Now, let's suppose your source is beta particles. What happens if you put increasing thicknesses of material between the source and the detector? At some point, all the signal stops because you will have reached the range of those beta particles. Suppose it's a source of alpha particles. What is enough to put between the source and the detector? A sheet of paper. So you have a source, you don't know what it is. You want to know if it's alpha, put a sheet of paper. It stops them all. It's beta, you put perhaps pieces of plastic, increasing pieces of plastic. Why not metal? Because you will be making X-rays. Don't put metal. Put plastic. Plastic will not produce X-rays or nothing relevant. So if with a sufficient thickness of plastic, you stop getting counts, it was beta. If it's gammas, put something like a metal, put lead, increase in thicknesses, and check the exponential, sorry. A high energy gamma ray, the drop is less pronounced. A low energy gamma ray, it drops faster. You understand? It's a very simple device. And yet, if you know how to use it, if you know what to do with it, you can get information. Play with this website. It's really well done. It allows you to do measurements, different materials, different sources. It'll be very, very educational. Shall we go for a short break? Good. Mezzo. Vorrei entro il 5:30. Perché ovviamente non sono chiusi solo loro. Dovranno pure io. Allora, intanto bisogna capire cosa c'è dentro, perché i Geiger contengono un gas che si chiama quencher, che serve a attenuare che è di due tipi, può essere di due tipi. O è un gas organico, che dopo un certo numero di colpi, tipo dipende da qualche milione di conti, finisce di essere efficace. Oppure è un alogeno, e quello però continua a funzionare perché separa e si ricombina dopo l'interazione. Credo che sia organico perché semplice, costa meno per questa.
Quindi sorgente di cui conosco precisamente il valore per vedere se la misura bene, però è una sorgente di cui è noto nuove
E
missioni.
tu vuoi sapere se lui sta progressivamente perdendo capacità, basta che tu ripeta la stessa misura 600 volte. Probabilmente non lo vedrai subito, lo vedrai se l'hai usato per tanto tempo, no, per mesi, per un anno. Quanto è grave?
Un parallelo capire, praticamente sono appassionato di orologi vintage e alcuni sono stati e quindi voglio vedere da quali stare lontano, perciò ho comprato questo strumento.
Hai sentito quello che raccontavo? Allora, tu l'hai aperto sto Geiger?
Basta, un cubo di cemento in cui metterli dentro, sì, per oggi corrado.
Per fa cosa? Per scavinare i gamma?
Tenerli, sì, non buttarli, schermarli.
Importante il Geiger te lo dici. Se tu fai la misura senza niente e poi alla stessa distanza, poi questo bianco che stavi dicendo, benissimo. Se riesci a... Ma anche a contratto dell'orologio.
Cioè, no, ascoltato l'orologio pochi sì,
Quindi la vedi una differenza? La vedi? Allora sì.
però non so se è misurata bene. Cioè, se quel
Misurata
valore
bene cosa significa? Se il pompeggio è una dose, quello lo fai se hai una sorgente nota.
questo è il problema.
Questo sì. Se ti vuole una sorgente nota calibrata,
Grazie mille.
no, sì, figurati. Tornando al discorso di prima, se ripeti la misura... Ah, questo volevo chiederti. L'hai aperto sto Geiger? Quanto è grande la parte del sensore?
Un cilindro
Quanto è piccolino?
3
Ok.
centimetri di base.
Ok. Quindi è molto piccolo. Essendo molto piccolo è possibile che tu veda, usandolo regolarmente per un anno o più, un po' di riduzione. Questo sì. Però devi fare sperimentalmente.
Va benissimo. Grazie mille.
Sì.
Grazie. Posso dire, non te lo dà. Alba tornerà oggi. Non so che
No, perché quei cantanti che sono molto in voga delle cose, non vuole offrire una formula semplice di
Grazie, ci vediamo dopo. Quanto ci deve?
Sì,
Mettere questo qui, vorrei creare una foto.
Stavo dicendo una cosa veramente più prima, cioè l'esplosione di coda nucleari. Sapevo leggermente diverso dell'esplosione in coda, cioè nel senso il discorso di radiazione è un effetto secondario che non è mai stato sfruttato in realtà nell'esplosione.
Concordo.
E l'esplosione in coda, però da quello che sapevo io, poi, in realtà si fa perché nella propagazione dell'onda di blast c'è l'interazione col terreno quando è in coda e il terreno genera a sua volta per rimbalzo un'onda
Un
e
po' come effetto suolo, tu intendi dire.
effetto suolo e si gioca sull'interferenza costruttiva per radere al suolo. Io così l'avevo sempre, però
Io credo che quello che dici sia sicuramente parte del quadro, ma l'altra cosa che io ho sentito dire, ma
era sulle radiazioni.
soprattutto il fatto che se l'esplosione la fai a terra, gli edifici schermano tutto, non solo le radiazioni. Se ho suggerito che
Sì,
fossero
no,
solo le
io
radiazioni,
ho capito, le
scherma
radiazioni.
tutto.
Sì,
Scherma
no,
tutto.
assolutamente
Cioè, gli
no.
edifici ti fanno già
No, no, sulla blast
da
wave,
protezione,
sì,
ti fanno da
sì.
protezione, capito? Quindi più ti arriva quasi perpendicolare, meno hai la protezione dagli
Sì,
edifici.
sì,
Questo era il punto.
sì.
Che vale per tutto, per tutte le radiazioni incluse come radiazioni meccaniche, onde
Certo.
meccaniche, onda
Certo.
alla o l'onda di pressione. L'effetto suolo e il fatto che sia massimizzata a quella distanza non l'ho mai sentito dire, ma è senz'altro vero.
Perché era quello che riporta quello per un po' la pellicola su
Io non mi interesso molto di
Noi siamo
progettazione.
no, progettazione no, però siamo qualche anno che ci stiamo focalizzando un po' nera sul discorso delle emergenze nucleari, però in Africa bellico. E stiamo lavorando con ISIN, abbiamo fatto un termine sorgente per la ridonazione di un ordigno di terreno in Ucraina per vedere il fallout in Italia. E diciamo c'è un libro che adesso mi sfugge di nome che riporta praticamente tutta la fisica.
Quindi più specificamente che l'effetto suolo
Sì, parla anche di un punto triplo un punto triplo non inteso nel senso di stato fisico, ma un punto triplo con la somma delle componenti, diciamo della stock wave quando c'è il rimbalzo al suolo e l'interferenza costruttiva. E,
no, ora questa cosa mi incuriosisce, me la leggo volentieri.
credo che posso, c'è pure
Te ne sarei grato, perché Io ho sempre sentito parlare del minimizzare l'effetto schermatura, ma,
Sì, no, questo
ma non solo in funzione di radiazione, è proprio tutto,
sì,
tutto, perché
sì, sì.
a quel punto l'onda viaggia senza incontrare ostacoli.
Sì,
D'altra parte, più sei lontano, più c'hai una riduzione, ci stanno sufficienti puntiformi. E addirittura fosse massimizzato l'effetto, ora che me lo dici, ha un senso la cosa, non l'avevo incontrato.
c'ho il link a tutti e due dei libri, diciamo, sono interessanti. Poi,
Bueno, no. Sto chiedendo come possa avvenire perché l'effetto suolo lo hai quando l'aereo atterrando, per esempio, a un certo punto crea questo cuscinetto, sai benissimo, no? Il cuscinetto è una pressione in cui l'aereo si appoggia perché stai comprimendo aria, mentre quando è in quota si appoggia, è un effetto di importanza dinamica, quando la comprime hai proprio maggior quantità di materiale che tiene infatti l'aereo si stabilizza
sì,
quando arriva
sì.
ad essere vicinissimo al suolo, aiuta tantissimo nell'atterraggio, tantissimo. Ci vuole una specie di presenza di due oggetti che ti fanno...
Però
e allora mi chiedo...
nell'uranio si parla di rebound del suolo, quindi è proprio il suolo che genera
Sì.
il riflesso dell'onda.
Sì, d'accordo. Mi chiedo cosa poi lo respinge giù.
Ah, beh, no, diciamo il rebound è,
No, forse siccome c'è un rilascio di energia che continua nel tempo, non è istantaneo.
sì,
Il flash di radiazione è istantaneo.
sì,
Il rilascio di energia avviene,
sì,
c'è una serie proprio anche di quasi di onde. Mi chiedo se quello vada a creare con l'onda che a quel punto continua a propagarsi, anche perché l'onda va verso l'alto e parte viene riflessa dall'atmosfera. Probabilmente c'è questa concomitanza. Lo leggo
sì,
volentieri.
sì,
Lo leggo volentieri. Se me lo mandi, te ne sono grato.
si chiama Glaston.
Ah, il Glaston, infatti è un nome che
Mi
conosco.
veniva
Glaston.
e poi c'è un altro fatto bene, un po' più succinto, che è un manuale del SIPRI. Il SIPRI è il servizio segreto svedese, che però ha fatto molta
Ed è
manualistica. Sì, sì.
Ok,
Eh,
interessa.
sì.
Grazie. All right, let's see if we restart. And I'd like to finish in about 1 hour, so we don't have to stretch it until 6, but leave a little sooner. But I'd like to reach some conclusions and show you some applications to the field of nuclear security in particular. So gas field detectors, we pointed, and I will skip some of the slides because I realized that I went slowly as I wanted to discuss certain things in detail. So I will skip some of the slides and I will distribute through Alba and the other managers of the course, I will distribute the PDF of what I've actually shown and actually discussed with you. We've seen that gas field detectors work in different modes. One of the modalities is current. So they measure a current that is proportional to the flow of radiation. Or they can work in pulse mode. When a ray comes, even a single ray, they measure the energy deposited. In so-called proportional mode, they allow you to recognize different types of radiation from the extent of the pulse. In Geiger mode, they do not, but they do give you a count rate that relates to the intensity of the field. If you play a little bit with materials between source and detector, you get additional information. So you need to be a smart user, even of a simple device like that. When a device works in pulse mode, as I said, we can analyze it. We can analyze the pulses, and based on their height, how big they are, we can correlate the pulse to the energy that is deposited. when pulses are counted, we need to make sure that the signal that is produced, see here you have the pulses of radiation and here is the signal. You want to make sure that the signal that is produced follows the pulses accurately. If the signal that is produced is much longer than the pulses, then the pulses may overlap. And then you lose the ability to resolve them one by one. This overlapping of the pulses causes what is called dead time, that is the inability to resolve the different pulses. I stop here, keep it simple. Okay, so let's get to the third type of detector. Remember we said counters, dosimeters, spectrometers. Let's look at spectrometers a little bit. In these devices, we do analyze the pulses, their height. We correlate it to the energy that is deposited. Sorry. So what we do is we take the pulses. These pulses come over time. We get this one, then this one, then this one. Well, let's analyze them differently. Let's analyze them in terms of how many times we get a pulse of this height or this height. And let's plot the frequency of pulses of different heights. This is called multi-channel analyzer. It produces a so-called pulse height spectrum. Okay, so we take the pulses and instead of just counting them over time, we say, okay, I got 1,000 of this height. I plot 1,000 here. I got 500 or 100 of this height. I put 100 here and so on. If we do that, when our detector is exposed to gamma rays, we see a distribution of pulses that looks like this. Here comes bigger pulses. So more energy deposited in the counter. When do you think that more energy is deposited by gamma rays? What is the effect that deposits more energy? Let's see if you remember something. Photoelectric, very good. So this is exactly the energy deposited by photoelectric interactions. Here instead is the energy deposited by Compton interactions. It's not a single energy. It depends on many things, the angle, etc. So if we want to analyze the signal and say, this is a source that emits gammas of, I don't know, 1 MeV, half an MeV, whatever, we need to focus on this part of the spectrum. And we would like this part of the spectrum to be as narrow as possible, so that if we have multiple gammas, we can recognize them. So we would like to have a high resolution, as it's called. The resolution is expressed by looking at this curve and looking at, in particular, at the width here. It's called full width at half max. So what we do is we take the maximum, we go down to 50% of the maximum, and there we look at the width of this curve. Full width at half max. We'd like it to be as small as possible. Okay? So this is the quantity that we use in so-called spectrometers. Let's look at the most important type of spectrometer, the SINC for gammas, the scintillator. Scintillators are devices that, when exposed to radiation, emit light. No longer a charge, light. They can be crystals, they can be ceramics, they can be plastics. They can be made to emit light. The mechanisms are different, but the result in the end is the same. A gamma ray comes, it interacts, it deposits energy, a lot of energy if it's photoelectric, less if it's Compton. This energy is converted to light. Light goes into all directions. We want to collect it here, because here we convert the light to an electrical signal with a device that is called photomultiplier. Once again, we get light and here we turn it into an electrical signal. Some of the light doesn't go to this interface here, but goes in the other direction. So around the scintillator, we place a reflector. It's like a mirror, but it doesn't produce an image. It just reflects the light. a material that can be used effectively is Teflon. If you stand in front of Teflon, you will not see your face, but it does reflect light. In particular, it reflects the wavelengths that are typically produced by these materials. So again, we can collect quite a bit of the light, even those rays that go away, maybe a total of 50, 60, 70% of all the light. Then here we convert that light into an electrical signal at the so-called photocathode. So the photons are absorbed, converted into electrons. So what is the effect that we have at the photocathode? We have a photoelectric effect. It's photoelectric. And on the other side of the photocathode, we have these photoelectrons. The photoelectrons are accelerated against different items that are called dynodes, many of them. And each time they strike a dynode, their number increases. In the end, the electrical signal is amplified by 1 million, roughly. It's a much stronger signal, much easier to measure. So what kind of materials do we want as scintillators? We want materials that emit light while the radiation is on. This is the profile, radiation is on, it stays on, and then it switches off. We would like the light to come out following the same pattern. Does it happen? No, it doesn't. Light is emitted increasing up to a certain value and then going down to zero. So there's always a little bit of a ramp and then a decay for the flashes of light. However, light is emitted during the irradiation. That is different from what we discussed before, thermoluminescence. In thermoluminescence, light is not emitted promptly, is only emitted when we later heat up the material. So the signal in this case is stored in the material. Here it is not stored. It immediately leads to the emission of light. Okay? So this is called radioluminescence because luminescence is emitted during the irradiation. This is called thermoluminescence because the light is only emitted later when you heat it up. This is good as a device that you wear to monitor your exposure, like you wear it for 2-3 months. At the end of the 3 months, you send it for reading. People put it in a reader, heat it up, get the light, which is an integral of the exposure received during those 3 months. But if you want a signal immediately, you need something like this, a scintillator. Scintillators exist in different types, organic and inorganic. Again, the time of the day and the level of detail are impossible to cover now. So let me just tell you, they can be materials that are crystals, inorganic, or there are materials that are organic molecules. The mechanisms for the production of light are different, but the result is similar. You get light when you expose them to radiation. That's the part that I will now quickly go through. One important point is when you make a crystal, it never comes out perfect. You may try hard, but it always comes out with some imperfections. The crystal may have some vacancies, missing atoms, or some atoms that are where they should not be. Have you ever played the game of musical chairs? I'm sure you have. So you have 10 people, 9 chairs, you stop the music, somebody is left without a chair, has to sit on someone's lap. So this atom here didn't find the chair because the crystal was formed, the melt solidified, and that atom had not found its spot. It got stuck. It sits on someone's lap where it shouldn't be. So this happens. This happens when you make the crystal. In principle, when you make a crystal, the temperature should be kept completely uniform while the crystal forms. It's almost impossible. Then what is it that we do? Because we cannot control easily the amount of these defects, we introduce defects on purpose. We put a lot of them, and we control the amount so that the intrinsic defects become irrelevant. Is that clear? We cover up the intrinsic defects by adding extrinsic defects. And thanks to these defects, we have the production of light through a mechanism that I will not discuss in further detail. The point is, we create energy levels that, when the material is irradiated by gamma rays, lead to the emission of light. And the amount of light correlates with the energy that is deposited. Let me just show you some properties of the scintillators. This is a busy table, but let's look at one type that is very common, sodium iodide. And here are the defects. This is thallium that is added as a defect, okay? It creates the defect. It's a dopant. Like athletes get doping, these crystals are doped with the addition of these materials. And the defects lead to the production of light. We want them to have a high density for intrinsic efficiency. We want them to have a high atomic number to get a lot of photoelectric effect. Remember, the photoelectric effect is proportional to Z, the atomic number, to the third. So the higher the atomic number, the more photoelectric. That's what we want. Then we have a so-called decay time, which means how long the flash of light is. This we want to be very short. We want the flash of light to be very, very fast so that you can have pulses one after the other and they don't overlap. Okay? So the best materials are those with a very short decay time. For example, this one here, LSO, this one here, or plastics. Plastics are very fast, very, very short decay time, but you see they have something we don't like very much. They have a low density and they have a low atomic number. So in plastics, you don't really get photoelectric effects. They're not very good for spectrometry. They tell you there are gamma rays, but they're not very good to measure their energy. Then we look at the photon yield. How many photons are emitted when 1 keV is absorbed? Now you see why we really like sodium iodide. It emits a lot of photons. It's a very bright scintillator. The more signal it produces, the better the counting statistics. We want an index of refraction that is similar to glass, because we will couple this piece of crystal to the photomultiplier, and the photomultiplier is inside a glass envelope, a glass bottle. So we want them to match one another. We would like it to be insensitive to humidity, not hygroscopic. And sodium iodide, unfortunately, is hygroscopic. So we need to put it in a hermetic container that is vapor-proof. Okay, these are the key points. And once again, it helps looking at this graph because it tells you based on energy and atomic number what you can expect. So let me now look at that line at 50. Here it is. This is sodium iodide. You see, sodium iodide gives us a lot of photoelectric, even for fairly high photon energy. So we do like it. All right, let's move on. The scintillator works like that. It produces the flash of light. We convert it to photoelectrons. We amplify the photoelectrons with the photomultiplier. A gamma ray of 0.5 MeV, that would be an annihilation photon. We'll create something like 20,000 photons by accounting for all those steps that I mentioned, the reflector efficiency, the conversion efficiency. Maybe we get 3,000 photoelectrons. We multiply that number by 1 million in the photomultiplier. The device looks like this: scintillator, photomultipliers, and then there's the rest of the electronics that conditions the pulse, bless you, and then amplifies the pulse. And then we analyze the heights of the pulses. Here's the photomultiplier, a bit more detail. You see the photoelectrons enter here, and they are in many steps increased in number, up to a factor of 1 million. That's the short of it. So we record the pulses, they come out with their different heights, we analyze them, we produce the spectrum, exactly as I told you before. This region from Compton, this region from the photoelectric effect. We like the photoelectric region to be very narrow so that if we have many sources, like here, we can recognize them. If the peak is not narrow, we will not be able to say what the different energies are. Okay? Let me skip a few things. Oh yeah, no, this is important. Please. So the Compton is not really a peak. The Compton is a continuum, as it's called. It's a broad region. Ideally, we'd like it to be not much. See, when we have a high atomic number, we maximize photoelectric and we minimize Compton. Because if you have almost all photoelectric interactions, there will not be much photoelectric Compton. That's what you want. So a high atomic number, very useful in these detectors if you want to measure the photon energy. Something you may wonder is, why is it that we get this broad peak? After all, the gammas have exactly the same energy, all of them. 662 if it's cesium, 511 if it's annihilation. They have one energy level. Why do we get a bell-shaped curve? Why is it not a single value? It's not because this light may be emitted in different positions inside the scintillator. So we can collect different amounts of light. It's not the light that is emitted, it's the light that is collected that produces that peak. So if we collect more, the peak, the signal will be on this side. If we collect less, it's on this side. And then we have a most probable value that is this. So we sort of calibrate the device, okay? And we call this maximum most probable value, we call it the energy of interest. For example, for technetium, 140 keV. That clear? Again, because of the collection of light. Let me skip a few more things and let me show you what can be done with these devices. We can see the difference between uranium. Now we're moving to our topics. We can see the difference between uranium that is highly enriched and uranium that is not. When uranium is highly enriched, it means that it's mainly uranium-235. Uranium-235 emits primarily this line here at 186 keV, very little above that. So if the spectrum looks like that, we have a sample of fuel or material that could be used for different things. This is a material that has a lot of uranium-235. If it also has uranium-238, let's remember what we said at the beginning. The half-life of uranium-238, 4.5 billion years. We have a lot of it, really a lot of it. Uranium-235 is only 0.7% of the total. So in nature, our samples will have a lot of 238 and very little 235. 235 is what's used both in reactors and in weapons, let's say. So if you want to make a weapon, you need highly enriched uranium. If you do spectroscopy with the devices that I've shown you, it'll look like this. If you have also uranium-238, it will look like this. And if you have different amounts of 35 of enrichment, this is a 93% enrichment, 10%, 3%, 2%, 0.7. This is natural uranium. You see how the spectrum changes. So these devices tell you what kind of uranium you're looking at. That's what we're interested in. They may also tell you if you're looking at plutonium after it's been in a reactor for a long time or not. Again, let me not focus on the details, but simply tell you spectra look different. They can be analyzed and we can determine the different amounts of different isotopes of plutonium, in particular 241 and 239. Okay, sometimes the spectrum looks like this. There's no photoelectric peak. When do you think we're getting this? That's a possibility. Another possibility is that beta emitter, but this, I have to agree with him, does look like a quantum region of a gamma spectrum. So what we're missing is the photopeak. What gives us the photopeak? When do we have a lot of photoelectric effects? High atomic number. When do we have a low atomic number? When the material is a plastic, organic scintillator. So if we're working with organic scintillators, the spectrum looks like that red line. We're missing the photopeak. Why would we want to work with the plastic if it doesn't give us that information? Because we can make really big detectors, really big, and we can monitor the passage of a truck and see if it emits gamma rays. Will we do high resolution spectroscopy? No, but we will be able to see radiation. And if we do detect something, because, we are surrounding the truck, so what type of efficiency is going to be high? Geometric efficiency. The truck goes through a gate. It's called portal device. It's like a door, portal device. It's a gate. The truck goes through it. We see everything and we scan it as it drives. Of course, we oblige the truck to drive slowly. It's a control speed type of a detector. And then if there's something suspicious, we tell the guy, hey, you pull over. We open the truck and we go with something else with a higher resolution. It's called secondary inspection. So they're very, very useful. Scintillators that are used are polyvinyl toluene. This is a plastic scintillator. The problem is they don't detect neutrons. We need something else. No time to discuss that now. When are they used? Well, in the US, they are the basis for the detection at the border crossing. So when cars, for example, drive from Mexico to the States, they go through this. You see all these columns? These are all scintillators, plastic scintillators. Yeah, they get monitored. These are the portal devices for cargo containers. So we can use them that way. Let me again skip a few things here. Can we, in principle, recognize if a plastic scintillator, detects neutrons? See, whenever you have plastic, you have hydrogen. And neutrons have almost the same mass as a proton, right? So now imagine a neutron striking a proton. You play billiard? You play pool? Some of you must do that. You know that if you hit the ball smack in the center, in principle, your ball stops and the other one is accelerated with the energy of your ball. Not exactly true because there's friction on the table, but let's say it's kind of true. So the first one stops and the second one accelerates. If you do that, you get protons that have high energy or the energy of the neutron and deposit their energy in the scintillator. So they will produce signal. The question is, can we recognize signal from neutrons versus signal from gammas? And the answer is yes, because their decay time is different. The pulses from gammas are much faster than pulses from neutrons. It has to do with changes in the spin of the electrons that are accelerated. But the point is, we can recognize the different pulses. So in principle, we can analyze the pulses and come up with this so-called pulse shape discrimination, whereby we see the signal produced by neutrons and the signal produced by photons. We can recognize them. It's a beautiful device. I'll go very, very quickly through the so-called semiconductors because I want to get to the applications and wrap up, possibly taking some questions. Semiconductors. What are semiconductors, first of all? You know that in nature we have different types of materials. Materials have crystals, have structures where you no longer see the energy levels of a single atom. The energy levels are discrete. They're the shells. When you start putting many atoms together, instead of having these discrete levels, you have bands of energy. So you have a band corresponding to the state occupied by the electrons. It's called valence band, occupied by the electrons. And then you have typically a gap in a material that is an insulator, a gap greater than 5 electron volts. And only if you bring electrons up here, they will be moving in that material. They will be in the conduction band. If you're looking at a metal, which is typically a conductor, a valence and conduction band overlap, which means electrons move. You apply a difference of potential, they move. Nothing stops them. If you apply a difference of potential to an insulator, what is an insulator? Can you give me examples of insulator? Ceramics, plastics. If you apply a difference of potential to a piece of plastic, nothing happens. In fact, if you want to touch something that has voltage applied to it, you use some plastic gloves, for example. They will not conduct. All right? So that will be an insulator. Even if you apply difference of potential, there will be no current flowing through. And then comes something intermediate, where there is a gap. It normally doesn't conduct, but you can give electrons enough energy to move. Those are called semiconductors. Now, we can play tricks with different types of semiconductors. We can couple different types of them and produce something. Sorry, I'm going to skip inevitably. Produce something that is like an ion chamber. Remember the ionization chamber that we described before. It will be a device where there is a region where there's no charge that can move. But if it undergoes exposure to radiation, then charges will be produced and they will move in opposite directions. We can record those charges and we get a lot of signal. Why do we get a lot of signal? Because the difference of potential is going to be in the order of a few electron volts. So now think about this. If you deposit 100 kilo electron volts, it'll produce a lot of signal, much more than in the other devices that we have described. So that peak that I've talked about will be much narrower. We will have a much greater resolution. You follow me? You ready to go to bed, huh? The point is simply, we have a device that is considered similar to an ionization chamber, but it has 3 advantages, at least, compared to an ionization chamber. It's a solid. Being a solid, it has a lot more interactions per unit mass compared to a gas, per unit volume compared to a gas. 2, typically it has a high atomic number, or it can have a high atomic number, and therefore it gives us a lot of photoelectric. 3, each time there is an interaction, we get a lot of signal. And then the peak is much narrower, gives us better resolution. Look at the spectra that we can get from these devices. Look how narrow the peaks are. They give us a very, very high resolution. This is the resolution for a source of americium, 60 keV rays, barium. This has multiple lines, cesium. Actually, this is cesium, 662 plus a pulsar reference, that's 662. We can use these devices for the final part of the class, conclusive part, that is for nuclear security applications. Let's define these nuclear security applications. They are the detection of radiological or nuclear threats. I think you all know that the world changed drastically after the September 11 attacks. All of a sudden, the West started getting very worried about a variety of possible tools, terrorist tools, that until then had not been really taken into serious consideration. The improvised nuclear devices, the possible diversion of special nuclear materials, uranium, plutonium, to make these bombs, or even radioactive sources that could be used for so-called dirty bombs. Many possible sources are available in the world. They could be stolen, they could be diverted. You don't need a lot of material. If you know what you're doing, you don't need a lot of material to make a weapon. In principle, some 4 kilograms of plutonium can be sufficient to make a bomb. 25 kilograms of highly enriched uranium. It sounds like a lot. They're actually very, very small volumes. The volume of 25 kilograms of highly enriched uranium, it's a sphere of 7 centimeters of radius. Very, very small, because the density is very, very high. So the IAEA has been tracking the possible diversion of these materials, creating a so-called illicit nuclear trafficking database. And over the years, they have seen the type of materials that are being trafficked. In these 10 years reported here, these are the types of sources that they've been tracking. This is only part of the picture. They don't know everything. Many things go undetected. Most of a significant number of these sources come from industrial or medical applications. So they're taken from there. But others contain materials that can be used to make weapons. And how could they be smuggled into a country like this? These are typical cargo ships that can carry thousands and thousands of containers that in principle could hide these materials. So in the US, before I showed you a partial picture of what they do monitor their borders, but they do more than that. They try to monitor these materials from their shipping ports. They try to get through their intelligence services information on whether this material is leaving a certain port. And if so, they try to detect the presence of these materials on cargo ships when the ships are still at large in international waters. Now, they don't have jurisdiction to board those ships in international waters, but they try to develop systems, detectors that do reveal the presence of these materials. The moment the cargo ships arrive, then they can examine them, for example, with those portal monitors that I've already shown you. Since September 11, they have invested a lot of money in developing scintillators with better performance. Here is sodium iodide that I've already commented. Look at all these materials. You see what improved? The resolution. So a lot of money has been invested in making detectors with much higher resolution. And let me show you why resolution is so important. One way to hide a material is not to put it in a container and shield it, but to put it next to another source, a source that is legitimate. For example, if you want to hide plutonium, something you can do, you put it next to iodine used for medical purposes. If your detector doesn't have a good resolution like sodium iodide, the peak from plutonium will fall inside the peak of iodine. You understand now why it's so important to have a high resolution. If you had a semiconductor like a high purity germanium, you would be able to see it very nicely. But see, high purity germanium is something you can use in the laboratory, not in the field. So there are intermediate solutions, devices based on cadmium zinc tellurides that are semiconductors. They're not as good as germanium, but they do have sufficient resolution to see the different peaks from the different isotopes of interest. You understand, the idea is developing devices that can be used in the field, possibly at room temperature. Final series of slides. Ideally, we'd like to know not only that there is a source and what it is, but where it is. That's not easy because, as we were commenting before, these photons are not visible photons. We don't get an image. We don't focus them with lenses. So there are special devices that can be used. We can use detectors for photons, and in front of them, we put a piece of metal with holes like this. In a special pattern, it's called coded aperture mask. When you do that, through complex mathematics, you can recognize the presence of sources, point sources, or even distributed sources, and you get an image of the radioactivity which you combine with an optical image. You understand, they're very complex devices. I don't know if any of you is familiar with nuclear medicine, something called gamma cameras. Have you ever heard of gamma cameras? They produce images of the radiation coming from patients. They do this. A patient containing radioactivity produces an image that looks like that. But here we can rotate the gamma camera. We do a scan. In this situation, you cannot do a scan. You just view the objects. So how do you recognize the position, the distribution? With these coded aperture masks. They're very complicated devices with a pattern of holes that look like that. And when different beams or sources irradiate that, they produce shadows that can be interpreted. So once again, coded aperture producing images. Another technique, it's called Compton imaging. We can use devices where photons scatter with Compton and then they stop. From the energy they deposit when they stop and the point where they interacted before, we can recognize the region they must have come from due to Compton scattering. That region is a cone. I will not go into the mathematics. If we record many of these cones and we look at the point of intersection, that tells us where the source is. Again, a complex device that now uses Compton. And as you can see, as you increase the number of counts, you can localize the source accurately. You can even localize distributed sources. This is a wall that's been contaminated with europium, and with a gamma camera, you can get a picture. It tells you where it is. That's for radioactive materials that emit gamma rays. How do you detect plutonium or uranium? They emit very little radiation. So one way to do it is to irradiate these containers with high energy X-rays. You cause fission in these materials, and then you try to measure what comes from the fission. Fission neutrons, for example. Fission produces a lot of neutrons. And here is the trick. I think I'll stop on this slide. If you have materials like uranium, plutonium, neptunium, and you irradiate them with X-rays, you can produce photofission. The maximum of photofission is up here. But if you use high energy photons, you will cause neutron production also in steel. You don't want that. So typically the interrogation, as it's called, is done with photons of a lower energy so that you trigger fission, not as much as at higher energies, but it's very clean and you can detect the presence of these materials. I see that you're tired. I understand that you're tired. I'm going to stop here. I'll send you these materials, but if you have any questions, I'll be happy to take them. All right. I thank you. I thank you. So mass spectrometry. It's a destructive technique. These are non-destructive techniques that you use at a distance. See, you want to do the analysis. This is, we just got a very good question. The question is, why don't we use mass spectrometry to identify the composition of the samples? And the reason is that you would have to take a piece of the material and bring it to the lab. What I've been describing to you are all techniques that can be deployed in the field and used possibly at a large distance from the object of interest. Good question. Exactly. In fact, you don't want to touch it. Yeah. Colomba, penso che tu mi senta ancora, penso che tu possa interrompere la registrazione.
What's your take on gamma cameras of first responders?
The devices with the coated aperture. Yes, there is a version that is developed that is portable. It uses cadmium zinc telluride.
In a company offering the price.
Yeah.
New thing. I don't know about the gamma cameras. Do you think it's useful?
It may be useful. It may be useful, depending again.
What are the problems?
At present, grazie mille a te. At present, the one limitation is the sensitivity. So if you want to examine a large area far away, the sensitivity is not the highest. It requires a long examination time. But again, it really depends on your specifications, your requirements. If you tell me what you need to do, I may be able to suggest some possible solutions. Yeah? Dubai? Okay.
Yeah.
Okay, I have contacts with the AD's, the Abu Dhabi Civil Defense Authority. It's in Abu Dhabi. I know it's your rivals. Good to have you back. Good to have you.
Too much information, but
I've been asked to do it in one day and it's a lot. I've tried to make it light.